far above the Earth, beyond the reach of clouds, weather, and the very pull of the familiar. There exists a place where light becomes an archive. It is not a metaphor. Every point of light in the night sky carries a physical record, a history written in photons that began their journeys long before our planet formed, long before life stirred, long before anything on Earth could have noticed them. By the time this light arrives at our eyes or our instruments, it is already ancient. A telescope looking outward never sees the universe as it is now. It only ever sees what the universe was. The farther away the light began its journey, the further back in time the view stretches. At the most extreme distances, the act of seeing transforms into a form of archaeology, a quiet, patient uncovering of cosmic history, one wavelength at a time. For most of human history, that deep history was inaccessible. The earliest stars, the first galaxies, the long, dark stretch before any structure emerged, these remained theoretical, hidden not by secrecy but by physics itself. As space expanded, light stretched, cooled and faded, slipping beyond the range of our instruments and our understanding. We were surrounded by a past we could not read. Then, slowly and with immense care, a new eye was built. An eye designed not for brightness or spectacle, but for patience. An eye tuned to the faintest warmth of ancient light. The James Webb Space Telescope does not rush. It waits. It collects. It listens to wavelengths that have been traveling for billions of years, carrying whispers from epochs when the universe was still learning how to shine. This is not a story about seeing everything. It is a story about limits, about how far back vision can truly reach, where observation must inevitably stop, and why those boundaries exist at all. It is about what becomes visible when human technology finally meets the fundamental structure of space and time. And it is, above all, about perspective. Because when you look far enough away, the universe stops feeling merely distant and starts to feel profoundly, unfathomably deep. So, welcome. If you enjoy calm, thoughtful journeys through science, you're in the right place. Take a moment to like this video and subscribe to the channel, it truly helps. And as you settle in, feel free to share where you're watching or listening from. After all, while this story stretches across billions of years and unimaginable distances, it always begins right where you are. Looking back is often described as something passive, as if the universe simply presents itself and a telescope quietly receives whatever arrives. But in astronomy, seeing is never passive. It is an active physical process, shaped and defined by motion, distance, and time itself. Every time a particle of light reaches an eye or a detector, something very specific has happened. A photon has been emitted somewhere, traveled through the void, survived interactions with dust, gas, and gravity, and finally transferred its energy into matter. A telescope does not simply observe an object, it intercepts light that has been on a journey. And that journey always, without exception, takes time. Light does not arrive instantly, no matter how empty space may seem. Its speed, while staggering by our everyday standards, is finite and fixed. This single, quiet fact reshapes everything about astronomy. Because if light takes time to travel, then seeing something far away is identical to seeing it long ago. This is not a metaphor, nor a poetic turn of phrase. It is a direct, inescapable consequence of physics. When light leaves a distant object, it begins a countdown, not toward decay, but toward arrival. The farther the distance, the longer that countdown lasts. By the time the light is gathered by a telescope, the event that produced it is already in the past. Sometimes by minutes, sometimes by years, sometimes by billions of years. This is why telescopes act as time machines without bending space, breaking causality, or violating physics. They simply wait. The idea feels strange only because everyday life hides the effect so completely. At human scales, light is so fast that the delay is negligible. When you look across a room, the light from the far wall reaches your eyes in a tiny fraction of a second. Even across a city, the delay is imperceptible. You do not feel as though you are seeing the past, but the delay is still there, woven into the fabric of perception. Look at a distant mountain on the horizon. and the light reaching your eyes left that mountain slightly earlier than the light coming from the ground beneath your feet. The difference is minuscule but real. You are already seeing a layered present stitched together from moments that are not perfectly simultaneous. Scale that intuition upward, and the effect grows quietly dramatic. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes a bit more than 8 minutes. If the sun were to suddenly vanish, the Earth would continue orbiting in absence for those 8 minutes, blissfully unaware that anything had changed, not out of ignorance, but because the information of its disappearance cannot travel faster than light. Light from the nearest stars takes years. Light from distant galaxies takes millions or billions of years. At those distances, the past is no longer a subtle blur, it becomes the entire view. This is where astronomy diverges from almost every other science. A biologist studies living systems as they are now. A chemist observes reactions unfolding in the present. But an astronomer never sees the universe as it exists at this moment. The universe does not offer that option. Every observation is delayed. Every image is historical. The further away the object, the older the information carried by its light. There is no clever workaround. No amount of mirror polishing or computational correction can make light arrive faster than physics allows. This sets a fundamental boundary, one that no telescope can ever cross. And that boundary is what makes the question of how far back we can see both profoundly meaningful and eternally constrained. It is tempting to think of telescope power in terms of raw ambition, bigger mirrors, better detectors, more sensitive instruments. And those things matter immensely. They extend our reach, sharpen clarity, and reveal fainter details. But they do not change the basic rule. A telescope cannot see events that have not yet had the time to send their light to us. This is why the earliest chapters of the universe are not hidden behind technological limitations, but behind physical ones. There was a time when there were no stars, no galaxies, no bright objects at all. Even if a telescope could be made infinitely perfect, there would still be nothing to see beyond a certain point. No light had yet been emitted. This is an important grounding idea because it shifts the question away from engineering bravado and toward cosmic structure. The universe itself decides how far back observation is possible. Scientists have understood this for over a century. As early as 1908, thinkers were wrestling with the consequences of finite signal speeds. Later, through the work of figures like Albert Einstein, it became clear that space and time are so deeply intertwined that observation is inseparable from history. Distance is not just where something is, it is when it was. Modern astrophysics builds on this understanding, not by trying to defeat it, but by working within it as carefully as possible. Organizations like NASA and the European Space Agency design telescopes with this reality in mind, not to reach the absolute beginning, which is impossible, but to push observation as close to the earliest luminous moments as physics will allow. That distinction matters. Because when people hear about seeing the early universe, it is easy to imagine peeling back layers as though time were a curtain that can be pulled aside at will. But time is not arranged like that. It does not open smoothly. It recedes in discrete steps defined by the appearance of light itself. Before the first stars formed, the universe was dark, not metaphorically, but literally. There were particles, radiation, and structure taking shape, but no glowing objects to illuminate space. No photons were being produced that could one day be collected by a telescope. So the act of looking back always involves a delicate balance between distance and brightness, between time and detectability, between what existed and what could announce its existence through light. What does reach us is fragile. Ancient light is faint. It is spread out over vast volumes of expanding space. It arrives stretched, cooled, and thinned. Capturing it requires patience, precision, and instruments designed to listen rather than to demand. This is why the idea of looking back should not feel triumphant. It should feel careful. A telescope does not conquer the past. It waits for the past to arrive. And this waiting is not passive. It involves cooling detectors to temperatures just a few degrees above absolute zero so their own heat does not overwhelm the faint cosmic signals. It involves positioning observatories far from Earth's warmth and interference. It involves calibrating instruments to distinguish an ancient photon from background noise. All of this immense effort exists in service of a single, simple act: intercepting light that has been traveling longer than life has existed on Earth. This is also why everyday language can be misleading. When images from deep space are released, they are often described as photographs. But what you are seeing is not a snapshot of a moment. It is a collection of arrivals gathered patiently over time, each photon carrying a timestamp set billions of years ago. The universe does not send updates, it sends echoes. Understanding this changes how the question of how far back we can see should be approached. It is not about pushing harder, it is about listening longer. It is about respecting the pace set by the cosmos itself. The limits are not arbitrary. They are woven into the fabric of reality. Light moves at its speed because space-time is built that way. Information propagates as it does, because causality demands it. These are not inconveniences, they are structural features of the universe, and paradoxically, they are what make astronomy possible at all. If light traveled infinitely fast, the night sky would collapse into a confusing, blinding simultaneity. Everything would be visible at once with no depth of time, no layered history. The universe would appear flat and static, stripped of its narrative. It is because light takes time that the universe has a story. Every distant point becomes a chapter, every faint glow becomes a record, and every telescope becomes an interpreter, translating arrival times into understanding. Before considering any instrument, any mission, or any discovery, this is the foundation that must be set. Seeing is an interaction. Looking back is a physical act. The past is not accessed by intention, but by interception. The universe reveals itself only at the speed it allows. There is a reason the speed of light appears so often in discussions about the universe. Not because it is dramatic or exotic or especially flashy, but because it quietly sets the pace for everything that can happen, be observed, or be known. Light does not merely move through space, it defines how space and time relate to one another. The speed at which light travels is not negotiable. It is not a preference of photons or a limit imposed by technology. It is a fixed property of space-time itself. No signal, no influence, no piece of information can outrun it. This single constraint governs causality. The simple, non-negotiable rule that causes must come before effects. It also governs observation, because observing something is nothing more than receiving information from it. And if information takes time to travel, then the universe can never be seen all at once. This idea becomes clearer, more tangible, when distance and time stop being treated as separate things. In everyday life, they feel distinct. A meter is not a second. A journey across town does not feel like a journey into the past. But at cosmic scales, that intuition breaks down completely. The framework that makes sense of this was developed in the early 20th century, most famously through the work of Albert Einstein. His theories of relativity reshaped how physicists understand motion, gravity, and time. But, for astronomy, one insight stands out above all others. Space and time are not independent stages on which the universe unfolds. They are woven together into a single, unified structure. In this structure, distance is inseparable from time. To move through space is also, in a very real sense, to move through time. And when light travels across the universe, it traces a path through this combined fabric, carrying both spatial and temporal information with it. This is why the speed of light matters so profoundly. It is not just a fast number. It is the conversion factor between space and time. It tells the universe how distance turns into delay. When astronomers say that a galaxy is billions of light years away, they are not just describing how far it is in space. They are also describing how far back in time its light began its journey. The two measurements are linked by the same constant. At small distances, this link is easy to ignore. At large distances, it becomes unavoidable. Look at a nearby star, and you are seeing it years ago. Look at a distant galaxy, and you are seeing it when the universe itself was much younger. At the largest observable scales, nearly everything visible belongs to the deep past. The present moment, the universe as it exists right now, is largely hidden from view simply because its light has not yet had time to arrive. This effect dominates astronomy in a way that has no real analogue elsewhere in science. There is no way to adjust for it. There is no correction that can be applied after the fact. The delay is built into reality, and it grows with distance. As observations extend farther and farther out, the difference between then and now becomes immense. Entire cosmic eras pass between emission and arrival. Stars are born and die. Galaxies merge and transform. The universe itself expands and cools, which introduces another subtle but crucial distinction. The age of the universe and the size of the observable universe are not the same thing. The universe is roughly 13.8 billion years old. That number describes how much time has passed since the universe emerged from its earliest hot, dense state. But the observable universe, the region from which light has had time to reach us, is much larger than 13.8 billion light-years across. This seems contradictory at first. How can something be older than its own age? The answer lies not in light breaking its own rules, but in the behavior of space itself. Space is not static. It stretches. As light travels, the space it moves through grows. This means the distance between where the light was emitted and where it is received increases while the light is in transit. The light did not travel faster than its allowed speed. Space simply expanded beneath it. As a result, the most distant regions we can observe today are now much farther away than 13.8 billion light-years, even though the light reaching us left those regions when the universe was much younger. This is why astronomers speak carefully about horizons. The observable universe is not everything that exists. It is everything that has had time to communicate with us since the beginning. Beyond that horizon, there may be more space, more galaxies, more structure, but no information from those regions can reach us yet, and some never will. This is not because of poor instruments. It is because of how space-time behaves. As distances grow and expansion stretches light waves, another effect becomes unavoidable. The light itself changes. As space expands, light waves are stretched along with it. Their wavelengths grow longer. Their energy decreases. Visible light emitted billions of years ago arrives not as visible light at all, but as infrared radiation. This shift is not optional. It is a direct, inescapable consequence of expansion acting on light during its long journey. At small distances, the effect is modest. At cosmological distances, it becomes extreme. Light that once carried the energetic signatures of hot, young stars arrives cooled, reddened, and faint. By the time it reaches Earth, it no longer sits anywhere near the range of human vision. This is where instrument design becomes inseparable from cosmic history. A telescope built only to observe visible light will simply miss much of the early universe. The information is still there, but is moved into wavelengths the instrument cannot detect. It is like trying to listen to a conversation that has drifted below the range of hearing. Turning up the volume does not help if the pitch itself has changed. Infrared detection becomes essential not because it is fashionable or advanced, but because the universe demands it. The deeper astronomers look, the more infrared the universe becomes. This is why modern observatories designed to probe the early universe focus so heavily on infrared sensitivity. They are not just looking farther, they are listening in a different register. This shift in perspective is important. It reframes the challenge of observing the early universe as one of alignment rather than conquest. The universe has already sent its messages. They are already on their way. The task is to build instruments capable of receiving them in the form they actually arrive. Understanding this also clarifies why there are absolute limits that no telescope can overcome. Even with perfect infrared sensitivity, even with infinite patience, observation cannot go back before light existed to carry information. The speed of light sets a hard boundary. Expansion stretches signals. Space-time itself decides which regions remain observable. This does not make the universe smaller. It makes it structured. There is a quiet elegance in this arrangement. The same rules that prevent instantaneous knowledge also preserve order. They ensure that cause precedes effect. They allow history to unfold rather than collapse into simultaneity. They give the universe depth. Without a finite speed of light, astronomy would lose its narrative. Everything would arrive at once. The night sky would flatten into confusion. There would be no sense of development, no layered past, no unfolding story written across distance. Because light is limited, the universe can be read. Each observation becomes a slice through time. Each image becomes a record of what once was. And each increase in observational reach carries astronomers not just farther away, but deeper into the universe's own history. This is why the speed of light is not merely a number to be memorized. It is the rule that gives the cosmos its shape. At first glance, the universe appears calm and still. The stars hold their positions. The constellations barely change. Even galaxies, when seen through a telescope, seem frozen in place. But this sense of stillness is deeply misleading. On the larger scales, the universe is in motion everywhere at once. This realization did not come easily. In the early 20th century, many astronomers assumed the universe was static and eternal, neither growing nor shrinking. Galaxies were thought to be fixed islands of stars embedded in an unchanging cosmic backdrop. Space itself was treated as a passive stage, not an active participant. That picture began to change through careful observation, not dramatic theory. In the 1920s, Edwin Hubble studied distant galaxies and noticed a remarkable pattern. The farther away a galaxy appeared, the faster it seemed to be moving away from Earth. Nearby galaxies drifted slowly. Distant ones receded rapidly. The very distant ones appeared to be fleeing at astonishing speeds. At first, this looked like a cosmic explosion, with galaxies rushing outward from a central point. But that interpretation did not survive closer scrutiny. There was no center. Every galaxy saw the same pattern. From any location, other galaxies appeared to be moving away. The only explanation that fit the data was more subtle and far more profound. Space itself was expanding. This distinction matters. Galaxies are not racing through space like debris from a blast. Instead, the distances between galaxies increase because the space between them stretches. Each galaxy remains relatively stationary within its local region, while the cosmic fabric beneath them grows. A helpful way to imagine this is to picture dots drawn on the surface of a slowly inflating balloon. As the balloon expands, the dots move farther apart. No dot is special. No dot sits at the center. Each dot sees all the others receding. The balloon is not a perfect analogy, but it captures the key idea. Expansion is not something happening inside space. It is something happening to space. Once this became clear, another consequence followed naturally. If space expands while light is traveling through it, then the light itself must be affected. Light moves as a wave. As space stretches, the wave is stretched with it. The distance between successive peaks grows longer. The light shifts toward longer wavelengths. This stretching is known as redshift. The term comes from visible light, where longer wavelengths appear redder to the human eye. But redshift is not limited to visible colors. It applies across the entire spectrum. Light that begins its journey as energetic ultraviolet radiation can arrive as visible light. Light that begins as visible can arrive as infrared. Light that begins as infrared can be stretched into radio waves. The key point is that the light does not disappear. It does not weaken because it is tired. It is transformed because the space it travels through has changed. This is why older light becomes harder to see, not because it fades into nothingness, but because it migrates out of the range our eyes evolved to detect. Human vision occupies a very narrow slice of the electromagnetic spectrum. It is tuned to the light emitted by a sun-like star, reflected off nearby objects within Earth's atmosphere. That narrow tuning works beautifully for survival. It is almost useless for deep cosmology. The early universe does not speak in visible light. The first stars and galaxies emitted light that was often bluer and more energetic than the light we see around us today. But after billions of years of travel through expanding space, that same light arrives stretched, cooled, and shifted far into the infrared. This has an important implication that is sometimes overlooked. The early universe is not dim because it was weak. It is dim because its light has been diluted across time and space, stretched thin by expansion, and shifted into wavelengths that ordinary telescopes cannot see. Trying to observe the early universe with visible light is like trying to hear a distant foghorn using ears tuned only for birdsong. The sound is still there. It simply exists in a register you're not equipped to perceive. This is why infrared astronomy is not optional for deep-time observation. It is mandatory. If a telescope cannot see infrared light, it will miss the most ancient signals the universe has to offer. No amount of image processing can recover information that was never detected in the first place. Sensitivity alone is not enough. The wavelength range must match the message being sent. This realization reshaped telescope design in fundamental ways. Earlier observatories achieved extraordinary things using visible and near-infrared light. They revealed galaxies in astonishing detail and pushed observation deep into cosmic history. But as astronomers pushed further back, they encountered a wall, not a sharp boundary, but a growing loss of information. The oldest galaxies appeared faint, red, and incomplete. Their light had shifted beyond reach. The universe was effectively whispering in infrared. To listen properly, astronomers needed instruments built from the ground up, with that reality in mind. Mirrors optimized not just for sharpness, but for collecting faint, stretched light. Detectors cooled to extreme temperatures so their own heat would not overwhelm ancient signals. Locations far from Earth's warmth and interference. This design logic is not about prestige or ambition. It is about alignment. The universe expands, light stretches, wavelengths shift. Therefore, telescopes must adapt. This chain of reasoning leads directly to the James Webb Space Telescope. Its emphasis on infrared observation is not a technological flourish. It is a direct response to cosmic expansion itself. James Webb was designed to operate where the early universe now resides in wavelength space. It does not chase visible photons that no longer exist. It listens for infrared ones that have been traveling since the universe was young. This is also why the telescope's images often look unfamiliar. Colors appear warm, golden, deep red. Structures feel softer, more diffuse. This is not an artistic choice. It is translation. Data collected in infrared wavelengths is mapped into colors humans can see, preserving relationships while acknowledging that the original light lies beyond vision. Understanding redshift makes this translation easier to appreciate. The colors represent history. The redness is not decorative. It is diagnostic. It tells astronomers how far the light has traveled and how much the universe has expanded since it began its journey. Redshift becomes a kind of cosmic timestamp. By measuring how stretched the light is, astronomers infer how much space has expanded. From that, they estimate how long the light has been traveling. Distance, expansion, and time become intertwined. This is why expansion is not a background detail in cosmology. It is the central mechanism that shapes what can be seen at all. Without expansion, the universe would look radically different. Light would retain its original wavelengths. The early universe might appear brighter and bluer, but without expansion, the universe itself would not resemble anything observed today. Structure formation, galaxy evolution, and cosmic history would all unfold differently. Expansion is not an inconvenience layered onto an otherwise static cosmos. It is the process that gives the universe its evolving character. And it is gentle. Despite the scale involved, expansion does not tear galaxies apart or stretch solar systems. Gravity dominates at small scales. Expansion becomes noticeable only across vast cosmic distances, where gravity weakens and space itself takes the lead. This gentleness is easy to miss, but it is precisely what allows ancient light to survive its journey. Photons are not ripped apart. They are stretched smoothly, carried forward on the slow swelling of space. By the time they arrive, they're older, longer, cooler, and quieter. But they are still intact, still carrying information, still able to tell a story. That story cannot be heard without the right instruments, which is why understanding expansion and redshift is not an abstract exercise. It is the reason certain questions about the universe can be asked at all. It explains why seeing farther back requires listening at longer wavelengths. And it reveals why the deepest views of cosmic history must be infrared by necessity, not by choice. The universe expands, light stretches, and observation adapts, or it falls silent. Light comes in many forms, even though human eyes only recognize a small fraction of them. What we call visible light occupies a narrow band, balanced neatly between shorter, more energetic waves and longer, gentler ones. Just beyond the red end of visible light lies infrared. Infrared light is not exotic or rare. It is everywhere. It is emitted by warm skin, cooling pavement, distant planets, forming stars, and the faint afterglow of the early universe itself. The only reason it feels unfamiliar is because human vision never evolved to see it. In physical terms, infrared light has longer wavelengths and lower energy per photon than visible light. That does not make it weaker in any absolute sense. It simply means each wave carries its energy spread out over a greater distance. Where visible light arrives in quick, tightly packed oscillations, infrared light moves with a slower, more relaxed rhythm. This difference turns out to be essential for astronomy. As light travels across the expanding universe, its wavelength stretches. Energetic light gradually becomes less energetic, not because anything drains it away, but because the space it travels through grows. By the time light from the earliest stars and galaxies reaches Earth, it has often been shifted completely out of the visible range. What once shone blue or ultraviolet arrives warm and red, or deeper still into infrared. This is why the early universe speaks infrared. The first generations of stars were massive, hot, and short-lived. They burned brightly, emitting large amounts of high-energy light. But that light began its journey when the universe was small, dense, and young. Over billions of years as space expanded, those wavelengths were stretched again and again. By the time they arrive here, they are no longer visible light at all. This transformation does not erase information. It changes the form in which that information arrives. And to receive it, telescopes must be designed to listen in the right part of the spectrum. There is another reason infrared light dominates the deep universe, and it has nothing to do with expansion. Everything with a temperature emits radiation. This is known as thermal radiation, and it applies universally. Hot objects emit more energetic light. Cooler objects emit gentler, longer wavelength light. A blazing star emits strongly in visible and ultraviolet. A warm planet glows in infrared. A cold cloud of gas, barely above absolute zero, emits in far infrared and radio wavelengths. The universe is old. On average, it is cold. As cosmic structures age and expand, their temperatures drop. The background glow of the universe itself now sits just a few degrees above absolute zero, radiating almost entirely in microwave wavelengths. Young stars and galaxies stand out against this background. But even they appear cooler once their light has been stretched across time. This means infrared telescopes are not only looking for stretched starlight, they are also naturally tuned to the temperatures that dominate much of the cosmos. Cold objects that are nearly invisible in visible light can shine brightly in infrared. Dust clouds, star-forming regions, and early galaxies often reveal their true structure only when observed at longer wavelengths. Dust plays a particularly important role here. Interstellar dust is made of tiny, solid grains composed of elements like carbon and silicon. These grains are extremely effective at blocking visible light. They scatter it, absorb it, and obscure whatever lies behind them. In visible images, dust lanes carve dark silhouettes across galaxies, hiding star-forming regions and distorting structure. But dust interacts very differently with infrared light. Longer wavelengths pass through dust more easily, slipping between grains rather than bouncing off them. Infrared light can penetrate regions that appear completely opaque in visible images, revealing stars and structures that would otherwise remain hidden. This ability transforms how astronomers see the universe. Star-forming regions that look like dark voids in visible light become rich, glowing landscapes in infrared. The dense cores of galaxies, often shrouded in dust, open up. Entire populations of stars emerge from what once looked like empty space. This is not a subtle improvement. It is a change in perspective. In the context of the early universe, dust becomes both an obstacle and a clue. Early galaxies rapidly enrich their environments with heavier elements, forming dust surprisingly quickly. That dust absorbed visible light and re-emitted it in infrared, further shifting the balance toward longer wavelengths. So even without cosmic expansion, infrared would still be essential. With expansion layered on top, it becomes unavoidable. This is where the limits of earlier telescopes come into focus. The Hubble Space Telescope revolutionized astronomy. It delivered images of breathtaking clarity and pushed observation deep into cosmic history. It revealed galaxies billions of light years away and mapped the large-scale structure of the universe with unprecedented precision. But Hubble was designed primarily for visible and near-infrared light. That choice reflected the scientific priorities and technological realities of its time. As astronomers pushed toward earlier epochs, they began to encounter a barrier. The faintest, most distant galaxies appeared redder and harder to resolve. Their light was slipping out of Hubble's most sensitive range. The telescope could see hints, suggestions, and partial structures, but not the full picture. This was not a failure of Hubble. It was a consequence of physics. The universe had shifted its language. To go further back, astronomers needed to listen where the universe was now speaking most clearly. That meant longer wavelengths. That meant colder detectors. That meant designing an observatory around infrared from the very beginning, rather than treating it as an extension of visible light astronomy. This realization shaped a new generation of instruments. Infrared astronomy requires special care. Infrared detectors must be kept extremely cold, or they will be overwhelmed by their own heat. The telescope itself must avoid warming from the sun, Earth, and even its own electronics. Observing infrared light is less like taking a photograph and more like listening for a whisper in a quiet room. The reward is access to a universe that would otherwise remain invisible. When astronomers look in infrared, they are not simply seeing farther. They are seeing differently. They are tuning into a wavelength range that carries the signatures of early star formation, hidden galactic cores, and ancient cosmic structures. Infrared becomes a bridge between eras. It connects the hot, energetic beginnings of stars and galaxies to their cooled, stretched present-day signals. It allows observation to keep pace with expansion rather than falling behind it. Understanding this makes the design choices of modern space telescopes feel less like bold gambles and more like careful responses. The universe expands, light stretches, dust obscures, temperatures drop. Therefore, observation must shift. Infrared is not an upgrade. It is a translation. It is the language the early universe uses now, after billions of years of travel. And any attempt to understand cosmic dawn without it would be like trying to read a story written in a script you refuse to learn. The universe has already chosen how it speaks. Astronomy simply listens. For many people, space astronomy is almost synonymous with the Hubble Space Telescope. For decades, it has shaped how the universe looks in the public imagination. Spiral galaxies suspended in darkness, nebulae glowing with intricate color. Deep fields crowded with countless distant galaxies, each a tiny smudge of light holding billions of stars. Hubble did not just collect data, it changed expectations. It transformed the cosmos from an abstract concept into a visual experience, something filled with structure, violence, and beauty on a scale that felt both awe-inspiring and intimately detailed. Scientifically, its impact has been just as profound. Hubble helped refine the expansion rate of the universe, revealed the large-scale structure of galaxies, traced the life cycles of stars from birth in dusty clouds to death in supernova explosions, and provided some of the clearest evidence for the mysterious force known as dark energy. It showed that the universe is not only vast, but richly structured, even at enormous distances, and that this structure follows physical laws we can observe and measure. But understanding how far back Hubble could see requires separating what it did exceptionally well from what physics quietly prevented it from doing. Hubble was designed primarily to observe visible light, with some ability to extend slightly into ultraviolet and near-infrared wavelengths. This made it extraordinarily powerful for studying stars and galaxies in a wide range of environments, especially those relatively close in cosmic terms. It could resolve fine details, separate tightly packed stars, and produce images of remarkable sharpness that felt almost tactile. When Hubble looked far into space, it could indeed detect galaxies that were billions of light years away. Its famous deep-field images demonstrated this dramatically. By staring at a tiny, seemingly empty patch of sky for days on end, Hubble revealed thousands of distant galaxies, each a fuzzy, reddish blob representing a different era of cosmic history. In that sense, Hubble could see very far back. It could gather light that had been traveling for over 13 billion years. But seeing something is not the same as seeing it clearly. The most distant galaxies Hubble detected often appeared as small, indistinct, reddish smudges. Their shapes were difficult to interpret. Their internal structure was largely unresolved. In many cases, astronomers could tell that a galaxy was there, but not much more than that. They could measure its approximate brightness and redness, but its true nature, its size, its mass, the types of stars it contained, its rate of star formation, remained shrouded in uncertainty. This was not because those galaxies were poorly formed or unusually faint by nature. It was because the light reaching Hubble had been stretched out to its most sensitive range. As galaxies become more distant, their light shifts toward longer wavelengths. The farther back the light originated, the more extreme this shift becomes. The galaxies formed during the universe's earliest periods. Much of their light arrives deep in the infrared. Hubble could detect the reddest edge of this light, but only barely. It was like catching the last few fading notes of a song as it slips below the threshold of hearing enough to know something is playing, but not enough to hear the melody, recognize the instruments, or understand the composition. This fundamental limitation arises from the interplay of three factors: mirror size, sensitivity, and wavelength range. Mirror size determines how much light a telescope can collect. A larger mirror gathers more photons, which is absolutely essential when observing extremely faint objects. Hubble's mirror, at just over 2.4 meters across, was a marvel of engineering for its time, but it set a finite ceiling on how much ancient light could be captured. Sensitivity determines how effectively detectors can register faint signals without being overwhelmed by noise. Hubble's instruments were extraordinarily sensitive for their era, but they still had limits imposed by the detector technology of the 1980s and 1990s, and by the constant thermal background even in space. Wavelength range determines which parts of the cosmic message can be heard at all. This is where the most fundamental constraint appeared. If light arrives outside the wavelengths a telescope is designed to detect, no amount of sensitivity or exposure time can recover it. You cannot hear a note that is outside the range of your microphone. These three factors do not act independently. They compound. As astronomers pushed Hubble toward earlier and earlier epochs, they encountered a narrowing window. The galaxies were fainter, their light was redder, and the signal increasingly slipped beyond Hubble's optimal range. Exposure times grew longer from hours to days. Uncertainty grew larger. Interpretation became more cautious. This gradual loss of clarity was not a surprise. It had been anticipated long before Hubble ever launched. Scientists understood that visible light astronomy would eventually run out of reach, not because of a lack of skill or effort, but because the universe itself shifts its signals as time passes. The early universe does not send its messages in the same wavelengths it once used. It translates them, through expansion, into a different part of the spectrum. In this sense, Hubble did exactly what it was designed to do. It carried astronomy to the very edge of what visible and near-infrared light could reveal. It mapped that boundary with remarkable precision, and that boundary, that frontier of fading clarity, became a guide. Rather than trying to push Hubble beyond its natural limits, astronomers used its results, the faint red smudges, the measured redshifts, the limits of detection, to define the requirements for a different kind of observatory. One optimized not for the universe as it looks nearby, but for how the earliest universe appears after billions of years of expansion, stretching, and cooling. This is where the James Webb Space Telescope enters the story. James Webb was never intended to replace Hubble. The two telescopes were designed to answer different questions, operating in different parts of the spectrum with different strengths. Hubble excels at sharp visible light imaging and long-term monitoring of nearby and intermediate distance objects, watching stars explode, planets transit, and galaxies collide in glorious detail. James Webb was designed to extend vision into deeper time, precisely where Hubble strained at the red edge of its capabilities. If Hubble showed us where the visible light path ended in a haze of redshift, James Webb was built to begin its journey in that haze. Its mission was to step into the infrared and listen. This was not a speculative gamble. It was a direct, calculated response to known scientific limits. Astronomers could already see where Hubble's reach ended. They could already estimate, from the redshifts of the faintest detectable objects, what wavelengths carried the information they were missing. The challenge was not deciding whether an infrared telescope was needed. It was deciding how far into the infrared it must go, how sensitive it needed to be to capture the faintest ancient light, and how to overcome the immense technical hurdles of building such an instrument. James Webb's larger mirror, its colder operating temperature, and its suite of infrared-focused instruments were all chosen to address these specific, physics-driven constraints. Each design decision traces back to a clear physical reason. Light from the earliest galaxies is exceedingly faint, therefore, the mirror must be as large as possible to collect more photons. Infrared signals are easily drowned out by thermal noise, therefore the telescope must be kept extremely cold. Cosmic expansion stretches light into long infrared wavelengths. Therefore, the detectors must be tuned to see those wavelengths with exquisite sensitivity. Seen this way, James Webb is not a leap into the unknown. It is a careful, deliberate continuation. Hubble showed what could be done with visible and near-infrared light. It revealed where clarity gave way to ambiguity. It provided the data that defined the next step. There is a quiet continuity in this progression. Science advances not by abandoning successful tools, but by understanding their boundaries. Hubble's limitations were not obstacles to be overcome blindly. They were signposts pointing toward deeper time. By recognizing those limits, astronomers did not diminish Hubble's legacy. They completed it. The universe does not yield its history all at once. It reveals itself in layers, each accessible only when observation aligns with physical reality. Earlier telescopes opened vast chapters of cosmic history. They also showed, with remarkable honesty, where the pages grew thin, where the ink faded. James Webb was built to read further, not because earlier efforts failed, but because they succeeded well enough to show exactly what was missing. Seeing deep into the past is not just a matter of pointing a telescope at the sky and waiting. It requires building an instrument that respects how the universe actually behaves. Light is faint. Space is cold and expanding. Time stretches signals until they barely whisper. To listen properly, the telescope itself must become an exercise in restraint, patience, and precision. This is the philosophy that guided the creation of the James Webb Space Telescope. From the very beginning, it was clear that no single country or agency could realistically build such an instrument alone. The scientific ambition was too large. The engineering challenges were too complex, the timescale was too long, and the cost too high. Instead, the project became one of the most significant international collaborations in the history of science, a partnership between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. This coordination was not symbolic, it was foundational. Each partner contributed essential components, expertise, and scientific leadership. Instruments, launch capability, detectors, and mission operations were divided deliberately, ensuring that the telescope reflected a shared global investment in understanding the early universe. The result is not just a machine, but a convergence of scientific priorities shaped by decades of prior discovery. At the heart of the telescope lies its most visually striking feature, the primary mirror. Mirror size matters enormously in astronomy, but not for the reason most people first imagine. Bigger mirrors do not primarily mean sharper images, though they help. They mean more light-gathering power. Ancient light is scarce. Photons emitted billions of years ago arrive at Earth, spread incredibly thin across a vastly expanded universe. By the time they reach a telescope, they are few in number, faint in energy, and easily lost in the sea of background noise. A larger mirror has more surface area to intercept those precious ancient photons. It is less about magnification and more about gathering power. The larger the collecting area, the more ancient light can be accumulated over time. improving both sensitivity and the confidence of detection. James Webb's mirror spans more than 6.5 meters across, giving it over 6 times the light-collecting area of Hubble's mirror. That difference is not incremental, it is transformative. Objects that would require weeks or even months of observation with Hubble to glean the faintest signal can be studied in hours with Webb, and with far greater detail. Faint smudges become resolvable shapes. Unreachable epochs become accessible. But building a mirror that large introduced a monumental practical problem. Rockets have finite size. A solid glass mirror 6.5 meters across simply cannot fit inside any existing launch vehicle. The solution was not to shrink the ambition, but to radically rethink the geometry. Instead of a single piece of glass, James Webb uses a segmented mirror composed of 18 individual hexagonal segments made of ultra-lightweight beryllium, coated in a thin layer of gold optimized for reflecting infrared light. Together, they form a single, precise parabolic surface, carefully shaped and aligned to act as one perfect eye. These segments had to be folded for launch, tucked compactly inside the rocket's fairing like a piece of cosmic origami. After launch, they would need to deploy, unfold, and align themselves in the cold of space with astonishing, nanometer-scale precision. Each segment is mounted on a suite of tiny motors and actuators, allowing engineers to fine-tune its position and curvature independently, shaping the mirror's overall figure down to incredibly small tolerances. This deployment was not a dramatic flourish. It was a necessity imposed by physics and engineering. Folding allowed for a large mirror without sacrificing launch constraints. Segmentation allowed for control, correction, and stability once in space. There is a quiet elegance in this design that mirrors the scientific goal itself. To see the early universe, light must be gathered patiently, piece by piece, and assembled into understanding. Mirror size alone, however, is not enough. Infrared astronomy brings a unique and formidable challenge. Everything that is warm emits infrared radiation. That includes stars, planets, people, and, unfortunately, telescopes themselves. If the telescope structure or its instruments are warm, they will glow brightly in the infrared, utterly overwhelming the faint cosmic signals they are trying to detect. It would be like trying to hear a whisper while standing next to a roaring jet engine. To avoid this, James Webb must be kept extraordinarily cold. Its instruments and mirrors need to operate at temperatures around 266 degrees Celsius, only about 40 degrees above absolute zero. At these temperatures, thermal noise drops to a negligible whisper, allowing the detectors to register the faint infrared photons arriving from the early universe rather than the telescope's own heat. Achieving this profoundly cold environment required another bold, non-negotiable design choice. Instead of orbiting close to Earth like Hubble, James Webb operates far away, at a location called the second Lagrange point, L2, about 1.5 million kilometers from Earth. Here, the gravitational pulls of the Earth and Sun balance in a predictable way, allowing the telescope to orbit the Sun in sync with Earth while maintaining a stable position. From this distant outpost, the telescope can keep its sunshield permanently oriented to block heat and light from the Sun, Earth, and Moon. The sunshield itself is a marvel of purpose-driven engineering. It is the size of a tennis court, made of 5 layers of a specially coated, wafer-thin material called Captain. Each layer is designed to reflect and radiate heat away into space. The sunshield works passively. By creating a series of temperature gradients, it allows heat to radiate out from between the layers, while preventing new heat from reaching the telescope. No active refrigeration is required for most components. The cold of deep space itself becomes the cooling system. This is engineering in service of listening. Every aspect of the telescope's design flows from a single overarching requirement: detect faint, stretched, ancient light without interference. Large mirror. Infrared optimized detectors. Extreme cooling. A stable, thermally pristine environment. Precise, active alignment. None of these features exist for their own sake. They are all direct, logical responses to the physical conditions imposed by deep time. The earliest luminous structures in the universe were not bright by modern galactic standards. They were small, chaotic, and embedded in environments thick with primordial gas and dust. Their light has traveled for over 13 billion years, stretched and thinned by expansion, diluted by distance. By the time it reaches us, it carries crucial information, but only just enough to be detectable above the universal background. James Webb was built to meet that challenge directly. This is why it is profoundly misleading to think of the telescope as a leap of faith or a speculative gamble. The physics was already known. Astronomers understood how light behaves, how expansion stretches wavelengths, and where earlier instruments like Hubble fell short. The telescope was not designed to chase surprises blindly, but to access a region of observation that physics clearly indicated existed, a region that was theoretically within our grasp if only we could build an instrument quiet enough, cold enough, and sensitive enough to hear. In that sense, James Webb is conservative in the best scientific way. It does not assume the universe will behave differently than our best models predict. It assumes the universe will behave exactly as physics suggests, and builds an instrument capable of listening accordingly at the wavelengths and sensitivities the universe demands. The international nature of the project reinforced this meticulous, evidence-driven mindset. Scientific consensus forged through decades of observation and debate guided every major design choice. Trade-offs were debated carefully in committees and review boards. Every gram of mass, every layer of shielding, every adjustment mechanism had to justify itself in terms of concrete scientific return. And the scientific return was always defined by one central, grounding question: how far back can observation realistically reach, given the laws of physics? Not how far back would be impressive, not how far back would sound dramatic in a press release, but how far back light itself allows. The telescope's engineering does not promise to reveal the beginning of everything. It does not claim to pierce all cosmic veils. Instead, it promises to approach the earliest luminous moments, the end of the cosmic dark ages and the dawn of the first galaxies, with unprecedented clarity, patience, and honesty. This restraint is its strength. By building a telescope that accepts the universe's limits rather than fighting them, astronomers created an instrument capable of operating right at the boundary between what can be observed and what cannot. The deep past does not announce itself loudly. It arrives faintly, slowly, and in infrared. James Webb was built to notice. Collecting ancient light, however, is only the first step. Once those faint, precious photons are gathered by the vast Golden Mirror and directed into the instruments, they must be interpreted. They must be translated from a dim, red-shifted glow into physical meaning. This is where James Webb's suite of instruments quietly does its most important work. The James Webb Space Telescope does not simply take pictures. It is, more accurately, a cosmic laboratory that measures light. Every observation is a carefully designed experiment to answer specific questions about what that light is made of, where it came from, and what happened to it along its billion-year journey. Among its most important tools are instruments such as the Near-Infrared Camera, NIRCam, and the Near-Infrared Spectrograph, NIR-SPEC. The names sound technical, but their roles are conceptually simple and deeply complementary. One shows where the light is coming from and what structures it reveals. The other dissects that light to explain what it contains, its composition, temperature, motion, and energy. NIRCam is responsible for imaging. It reveals structure. It transforms faint, unresolved smudges into shape-showing galaxies as clusters, arcs, and irregular forms rather than mere points of light. Through NIRCam, astronomers can map where ancient light is arising from and how it is distributed across the sky. It provides the context, the cosmic landscape, but images alone, no matter how sharp, are not enough. A galaxy's shape can tell you something about its size and gross structure, but very little about its composition, its history, or the physical conditions within it. To understand what a distant object is truly made of, how hot it is, how fast it is moving, or how energetically it is forming stars, astronomers must look beyond brightness and shape. They must look inside the light itself. This is where spectroscopy enters and where NIR-SPEC becomes indispensable. Spectroscopy is the practice of separating light into its component wavelengths, spreading it out into a spectrum, a rainbow, if you will, though often one our eyes cannot see. Instead of treating light as a single blended glow, A spectrograph disperses it, revealing how much energy arrives at each specific wavelength. The result is not a picture in the usual sense, but a patternograph of intensity versus wavelength. This pattern carries an extraordinary amount of information, encoded by the laws of atomic and molecular physics. Different atoms and molecules interact with light in specific, predictable ways. They absorb certain wavelengths and emit others. These interactions leave distinctive marks in the spectrum, often described as spectral lines or fingerprints. Hydrogen leaves one pattern, oxygen leaves another. Carbon, nitrogen, iron, countless elements and molecules each imprint their own unique signatures. By studying these patterns in the light from a distant galaxy, astronomers can identify which elements are present, even if that galaxy lies billions of light-years away. This is not guesswork. These spectral fingerprints are measured with extreme precision in laboratories on Earth and have been confirmed through decades of astronomical observation. The same hydrogen that glows in a laboratory plasma tube produces the same spectral pattern in a galaxy at the edge of the observable universe. Physics does not change with distance. Through instruments like NIRSpec, James Webb can take the faint, redshifted infrared light from an ancient galaxy, disperse it into a spectrum, and read these fingerprints with remarkable sensitivity. A faint galaxy that appears as nothing more than a soft, golden-hued glow in a NIRCam image suddenly becomes a rich source of chemical information. From its spectrum, astronomers can learn what the earliest galaxies were made of. They can determine whether a galaxy contains only the simplest elements, hydrogen and helium, forged in the first few minutes after the Big Bang, or whether it has already been enriched by previous generations of stars that lived, died, and scattered heavier elements like carbon and oxygen into space. This distinction matters deeply. It tells scientists how quickly the cycle of starbirth and death began in the early universe. A galaxy with heavy elements is not among the very first. It is a second or third generation system, already bearing the ashes of earlier stars. Spectroscopy also reveals temperature. Hot objects emit light differently from cool ones. The overall shape or continuum of a spectrum carries information about the temperature of the emitting source. A population of massive hot blue stars produces a different spectral signature than a population of cooler, redder, older stars. In this way, astronomers can infer whether an early galaxy is dominated by a frenzy of young, massive star formation or contains a more mature, settled mix of stellar ages. They can estimate how actively stars are forming and how much ultraviolet radiation, the kind that can ionize atoms and shape galactic environments, is being blasted into space. Motion, too, is encoded in the spectrum. When an object moves relative to the observer, the wavelength of its light shifts slightly due to the Doppler effect. Light from an object moving away from us appears stretched toward longer wavelengths, redshifted further. Light from an object moving toward us appears compressed toward shorter wavelengths, blue-shifted. For distant galaxies, the dominant motion is due to the expansion of the universe itself, which produces the cosmological redshift that tells us how much the universe has stretched since the light was emitted. But finer spectral analysis can also reveal internal motions, the rotation of a galaxy, the outflow of gas from supernovae, or the turbulent churning within its interstellar medium. For the most distant galaxies, the overall redshift becomes a powerful clock. The amount of stretching in the spectrum reveals directly how much the universe has expanded since the light began its journey. From that, combined with our model of cosmic expansion, astronomers estimate not just a distance in light years, but a look back time how long ago the light was emitted. Distance and age emerge not from a direct tape measure measurement, which is impossible, but from reading the history written into the very structure of the light itself. This is one of the most subtle and elegant aspects of astronomy. No ruler spans billions of light years. No stopwatch can be sent into the past. Instead, light arrives carrying its own meticulous record of the journey. James Webb's instruments are designed to read that record with extreme care. This is especially critical when dealing with the earliest, faintest galaxies. These objects are not just distant, they are intrinsically small and often irregular. Their light arrives weakly, sometimes just a hair's breadth above the background noise of the universe itself. Turning that whisper of a signal into reliable quantitative data requires not just sensitivity, but extraordinary stability and precision in measurement. By combining the imaging power of NIRCam, which tells astronomers where to look and helps isolate the light of a specific, faint galaxy from its neighbors, and the foreground with the analytical power of NISPEC, astronomers can execute a powerful sequence. First, identify a candidate distant galaxy in an image. Second, point the spectrograph at it. Third, collect its light for hours, dispersing it to reveal the spectral lines. The image provides the where. The spectrum provides the what. Together, these measurements transform a vague reddish shape into a physical system with measurable properties. A galaxy stops being just a point of light and becomes a collection of stars, gas, dust, and motion. Its chemical makeup hints at how many generations of stars preceded it. Its temperature reveals how violently it is forming new stars. Its spectral redshift places it at a specific, quantifiable moment in cosmic history. This is why James Webb's instruments are so central to its mission. They are not accessories, they are interpreters, translators of the cosmic language of light. The telescope does not simply look deeper than before, it understands more deeply. This distinction matters profoundly because early observations of the distant universe, with Hubble and other telescopes, often involve significant ambiguity. A faint red object in an image might be a very distant young galaxy, or it might be a closer, older galaxy that is simply reddened by vast amounts of dust. Without spectral information, the difference can be nearly impossible to resolve. Spectroscopy cuts through that uncertainty like a knife. By identifying specific absorption and emission lines, astronomers can distinguish between the redshift of distance and the reddening of dust. They can place objects accurately within the timeline of cosmic history, rather than relying on educated guesses based on appearance alone. This careful, evidence-based approach reflects a broader scientific philosophy that underpins modern cosmology. Claims about the early universe must be grounded in measurement, not in impression or hope. The further back observation reaches, the more cautious interpretation must become, because the stakes of being wrong, of misinterpreting a signal, of misjudging a distance are higher. James Webb's instruments were built with this necessary caution in mind. They allow astronomers to test ideas rather than assume them, to measure rather than infer loosely, to confirm that what appears ancient and distant truly is ancient and distant. In doing so, the telescope turns observation into a dialogue. Light arrives from the past, carrying data. Instruments separate it, analyze it, and translate it into information. Astronomers listen, compare the results to predictions from theories and simulations, and revise their understanding accordingly. The universe does not offer simple answers. It offers complex, often noisy, but ultimately decodable data. By measuring ancient light rather than merely displaying it, James Webb ensures that the story of the early universe is told not as speculation or wondrous myth, but as evidence-based narrative. Each spectrum becomes a fragment of cosmic history, preserved not in stone or ancient text, but in the immutable structure of light itself. And once light can be read this way, distance and age stop being abstract, philosophical concepts. They become measurable properties, encoded quietly in every photon that arrives, waiting for an instrument patient and precise enough to decode them. In everyday life, distance is something you can measure directly. You can pace it out, stretch a tape across it, watch numbers tick upward on a car's odometer, or send a radar pulse and time its echo. Even when distances grow large, from cities to continents to the moon, the basic idea remains. You measure from here to there, and you trust the tool in your hand or the physics of your instrument. Astronomy offers no such convenience. No ruler reaches into interstellar space. No probe has traveled billions of light years to plant a flag and radio back its location. Instead, astronomers must become cosmic detectives, inferring distance indirectly by reading the clues carried by the light itself. Distance is not so much measured as it is reconstructed, pieced together from a chain of interdependent observations and well-tested physical principles. It is a fundamental act of scientific translation, turning the language of light into the language of location and time. One of the most important of these clues, as we have seen, is redshift. But to understand its full power and its limitations, we must delve a little deeper. As light travels through an expanding universe, its wavelength stretches in proportion to how much the universe has expanded during the journey. This is not a mere optical effect. It is a direct imprint of cosmic history on the photon. The amount of stretching depends integrally on the distance traveled. The farther the light has come, the more space has expanded beneath it, and the more its wavelength will have grown. By carefully measuring how shifted specific spectral features are comparing the observed wavelength of, say, a hydrogen emission line to its known rest wavelength measured in a lab, astronomers can calculate a redshift value, denoted by the letter Z. This number is key. A redshift of Z(x1) means the universe is expanded by a factor of 2 since the light was emitted. The wavelength observed is double its original length. A redshift of ZT9, which James Webb is now routinely probing, means the universe has expanded by a factor of 10. The observed light is stretched to 10 times its original wavelength. This redshift value does not by itself give a distance in light years. It provides a relationship between expansion and time. To convert that into a distance, astronomers must employ a model of cosmic expansion, a mathematical description of how the universe's expansion rate has changed over its 13.8 billion year history. This model is not guesswork. It is the lambda cold dark matter (VDM) model, the prevailing and extraordinarily successful cosmological framework that has been refined over decades by observations of the cosmic microwave background, large-scale galaxy surveys, and supernova studies. Plugging a redshift value into this model yields both a look-back time, how long ago the light was emitted, and a co-moving distance, how far away the object is now, taking into account the expansion that occurred during a light's travel. This is how a spectrum becomes a timestamp and a map coordinate. It is a profound inference. By analyzing the stretch of ancient light, we can place a galaxy not only in space, but also in time, pinning it to a specific chapter of the cosmic story. Redshift alone, however, is not always enough for the most robust distance measurements, especially when building the foundational distance ladder that anchors our entire cosmic scale. Brightness provides another crucial, independent piece of information. Light obeys the inverse square law. As it travels, it spreads out uniformly in all directions. The farther it goes, the thinner and fainter it becomes. If astronomers know how bright an object truly is, its intrinsic luminosity, and how bright it appears from Earth, its apparent brightness, they can immediately estimate how far away it must be. This is the same intuitive logic you use when judging the distance of a streetlight at night. A light that appears dim could be a weak bulb nearby, or a powerful beacon very far away. To decide which, you need more context. In astronomy, that context comes from objects whose intrinsic brightness is well understood and remarkably consistent. These celestial landmarks are known as standard candles. A standard candle is an object or event whose physics dictates a predictable, known luminosity. If you can identify such an object in a distant galaxy, its observed brightness becomes a direct measure of distance. The universe, in its generosity, provides a few such reliable beacons, and among the most important for cosmology are a specific class of stellar explosions, type Weyr supernovae. These occur in binary star systems where a dense white dwarf star accretes matter from a companion until it reaches a critical mass threshold, triggering a thermonuclear explosion that completely disrupts the star. Because this critical mass is always nearly the same, the resulting explosions have a remarkably consistent peak intrinsic brightness. A type Weyr supernova can, for a few weeks, outshine an entire galaxy of hundreds of billions of stars. By carefully measuring how bright such a supernova appears from Earth and knowing how bright it should be at its peak, astronomers can calculate its distance with stunning precision, even across billions of light years. These supernova measurements have played a central, revolutionary role in modern cosmology. In the late 1990s, by using type PR supernovae as standard candles to measure distances to faraway galaxies, two independent teams made a shocking discovery. The most distant supernovae were fainter than expected, meaning they were farther away than the prevailing model of a steadily decelerating universe predicted. The only plausible explanation was that the expansion of the universe is not slowing down due to gravity, as everyone thought, but is actually speeding up. This led to the Nobel Prize-winning discovery of dark energy, the mysterious force permeating space and driving this accelerated expansion. Organizations like NASA and the European Space Agency have supported decades of dedicated supernova surveys, precisely because of their irreplaceable value as cosmic mile markers. They provide the critical rungs in the middle of the distance ladder, bridging the gap between nearby measurements using parallax and other techniques and the extreme redshifts of the early universe. Spectral features themselves add yet another layer of confirmatory information. The specific pattern of absorption and emission lines in a galaxy spectrum does more than just yield a redshift. The relative strengths and widths of these lines can reveal the object's physical conditions, its temperature, density, chemical composition, and even the velocity dispersion of its stars or gas. These details help confirm the nature of the object. For instance, they can help distinguish a genuinely young, distant galaxy from a closer, dusty galaxy masquerading as one. They provide a cross-check, ensuring that the redshift is cosmological and not caused by some other, more local dynamical effect. Given these tools, redshift, standard candles, spectral diagnostics, one might think measuring cosmic distances is straightforward. It is not. In practice, distance estimation in astronomy almost never relies on a single, perfect method. Instead, it is built as a carefully interconnected structure known as the cosmic distance ladder. The ladder is a sequence of methods, each calibrated by the one below it, allowing astronomers to step progressively further out into the cosmos. The first rung is the most direct, stellar parallax. By observing a nearby star from opposite sides of Earth's orbit around the Sun, 6 months apart, astronomers can measure its tiny apparent shift against the backdrop of much more distant stars. This geometric method gives a direct, model-independent distance for stars within a few thousand light-years. These parallax measurements, now delivered with exquisite precision by spacecraft like ESA's Gaia mission, calibrate the properties of certain types of stars like Cepheid variable stars, whose intrinsic brightness can be determined from their pulsation periods. Cepheids then become a new class of standard candle, visible in nearby galaxies. Once Cepheids in a galaxy are measured, they calibrate the peak brightness of Type 1 supernovae that occur in the same galaxy. Since supernovae are vastly brighter, they can be seen in galaxies much farther away than Cepheids. Thus, the supernovae become the next rung on the ladder, reaching out to billions of light-years. Finally, at the greatest distances, where even supernovae are too faint to detect routinely, astronomers rely primarily on redshift derived from spectra, but this final step depends critically on the lower rungs. The entire Thion CDM model that converts redshift into distance and time is itself constrained by the supernova data and other measurements. The ladder is a closed, interdependent loop of evidence. Each rung supports the one above it, and the entire structure is tested for consistency at every turn. This layered approach is powerful, but it is not perfect. Uncertainty is an inescapable companion. Error and uncertainty accumulate as you climb the ladder. A tiny imprecision in a parallax measurement propagates upward into the calibration of Cepheids. A slight scatter in Cepheid properties affects the supernova calibration. Assumptions that are safe and well tested in nearby galaxies about stellar populations. Dust absorption, or the uniformity of standard candles become harder to verify at extreme distances. As observations push deeper into cosmic history, into the realm of James Webb, this inherent uncertainty grows. The objects are at the very limit of detectability. Their light is drowned in noise. Their spectral features are weak and blurred. Models of their intrinsic brightness rely ever more heavily on theoretical assumptions about how stars and galaxies behaved in the early universe, assumptions that James Webb itself is testing for the first time. Even our knowledge of the universe's expansion history introduces a layer of uncertainty at these extreme redshifts. Professional astronomers do not hide this uncertainty. They quantify it, embrace it, and report it transparently. Distances to the earliest galaxies are never stated as a single, precise number. They're always given as a range. A galaxy might be placed at a redshift of z equals 10.2 plus rines, which corresponds to a look-back time of roughly 13.3 billion years, plus or minus 100 million years. Its distance might be expressed as a co-moving distance of about 32 billion light-years, with a significant margin of error. These ranges and error bars are not signs of weakness or ignorance. They are expressions of scientific honesty and rigor. They represent the current frontier of knowledge, with its edges honestly acknowledged. There is a temptation, especially outside of science, to seek absolute answers, a single definitive number, a sharp boundary, a clear-cut first. But the universe does not always cooperate. At great distances, precision naturally gives way to probability. This is why the question, how far back can we see, is never answered with a single, sharp line. Instead, it is described as a gradual approach toward a physical limit, with increasing uncertainty and richness of interpretation as that limit is neared. And this uncertainty is not merely tolerated, it is informative. It defines the space where discovery happens. When observations fall neatly within the expected range, confidence in our models grows. When they fall outside, when a galaxy appears surprisingly bright, massive or evolved for its redshift, it is not automatically a crisis. It is an invitation. Uncertainty becomes the fertile ground where theories are tested, stretched, and refined. This is particularly true for the observations now flowing from the James Webb Space Telescope. Webb operates in a regime where the light is not just faint, but profoundly transformed, stretched by a factor of 10 or more, carrying the signatures of environments that have no modern analogues. It observes objects that sit right at the precipice of detectability. In this realm, small differences in data processing, calibration, or interpretation can have large consequences. A slight shift in the estimated redshift of a faint, noisy spectrum can move a galaxy hundreds of millions of years closer to or farther from the theoretical moment of cosmic dawn. A different assumption about the galaxy's star formation history can change the inferred mass by a factor of 2. Rather than avoiding this ambiguity, astronomers lean into it with a disciplined methodology. Multiple independent observations of the same target are combined. Data from different instruments on Webb cross-check each other. Independent research teams around the world download the same public data and analyze it with different software pipelines and assumptions. Initial claims, often made with appropriate caution in preliminary papers, are revised, refined, and sometimes withdrawn as more data accumulates and analyses converge. This process can feel slow and cautious from the outside, far from the dramatic eureka of popular imagination. But it is precisely this meticulous, collective scrutiny that allows robust confidence to build over time. The farther back observation reaches, the more vital this caution becomes. The earliest galaxies are not just more distant versions of the galaxies we see nearby. They are different. Their stars, gas and dust exist in a younger, denser, more chaotic universe. They behave in ways that can challenge models built primarily from observations of the mature, settled cosmos around us. Applying familiar assumptions too rigidly can lead to serious misinterpretation. Recognizing and quantifying uncertainty acts as a safeguard against that. It forces a healthy humility and keeps interpretations flexible. This mindset also reshapes what it means to measure something at the edge of the observable universe. Distance stops being a single crisp value. It becomes a range of possibilities constrained by the available evidence. A galaxy's age becomes an interval within cosmic history, not a specific date. Its location becomes a probability distribution in an expanding space-time, not a fixed point on a static map. This may sound abstract, but it accurately reflects how the universe presents itself at these extreme scales. The information arrives incomplete, filtered through billions of years of expansion and the limitations of our detectors. Interpretation must remain fluid, always ready to be updated by the next, better measurement. James Webb, by its very design, pushes observation into a realm where these limitations are not flaws to be lamented, but fundamental features of the quest. The uncertainty itself becomes a source of insight. When a galaxy appears brighter, more structured, or more chemically enriched than the simplest models predicted for its redshift, The immediate question is not, is our measurement wrong? Though that is always checked first. The more productive question is, what does this tension teach us about the early universe? Perhaps gas cooled and collapsed into stars more efficiently than we thought. Perhaps the earliest star formation was even more frenetic and prodigious. Perhaps small galaxies merged into larger ones with startling speed. Or perhaps our understanding of how to convert a faint infrared signal into a stellar mass needs revision. Each possibility is a pathway to deeper understanding. By measuring distance without rulers, astronomers accept a profound truth. The universe does not reveal itself all at once, or with perfect immediate clarity. It offers hints, patterns, and probabilities. It invites careful, iterative reading rather than instant, dogmatic conclusion. And as observation presses closer to the earliest luminous moments, the ultimate horizon of starlight, this careful, humble, and uncertainty-aware reading becomes the most valuable scientific tool of all. The universe does not demand or reward false certainty. It rewards patience, precision, and the courage to let evidence guide understanding, even when it leads into unfamiliar and surprising terrain. For a long time, the earliest galaxies existed only in theory and in the glowing pixels of supercomputer simulations. Astronomers could describe them mathematically, model their growth in intricate virtual universes, and infer their properties from the later galaxies they would evolve into. But they could not see them directly. They were predictions waiting for confirmation. Those predictions were not arbitrary fantasies. They emerged from the rigorous application of known physics, gravity, gas dynamics, thermodynamics, and nuclear processes to the unique initial conditions of the young cosmos. According to these models, the first galaxies were not grand, majestic spirals or smooth, featureless ellipticals. They were small, irregular, and turbulent. They formed in a universe that was still finding its balance, where matter had only recently begun to clump together under the relentless pull of gravity. In the first several 100 million years after the Big Bang, matter was distributed almost uniformly, with only tiny quantum mechanical ripples in density. Gravity, acting over cosmic time, amplified these ripples. Slightly denser regions pulled in more gas and dark matter, growing slowly at first, then faster as their gravitational pull increased. This process did not produce neat, isolated spheres. It produced a cosmic web, vast filaments of dark matter intersecting at dense nodes, with ordinary gas flowing along these invisible highways. The earliest galaxies emerged within the densest of these nodes and intersections. They were modest by today's standards. Many contained the mass equivalent of only a few billion stars, a mere 1% of the Milky Way's stellar mass. Their shapes were not symmetrical. They were clumpy, fragmented, and constantly changing, shaped by frequent mergers with neighboring proto-galaxies and by powerful winds from their own exploding stars. This inherent chaos was not a bug. It was a defining feature of the era. Early galaxies formed in an environment awash in pristine primordial gas. This gas was almost purely hydrogen and helium, the simplest elements forged in the universe's first 3 minutes. Heavier elements like carbon, oxygen, and iron, which astronomers collectively call metals, had not yet been produced in significant quantities because stars had only just begun to form, live, and die. This chemical simplicity had profound consequences. In modern gas clouds, trace amounts of metals allow the gas to cool efficiently by radiating away heat. This cooling lets the cloud fragment into many small, dense clumps, leading to the formation of stars of all sizes, from small red dwarfs to massive blue giants. In the metal-free early universe, however, the gas could not cool as efficiently. It tended to collapse into larger, monolithic blobs. As a result, the very first generation of stars known as Population 3, stars are thought to have been behemoths, tens or even hundreds of times more massive than our Sun. These stars would have burned ferociously hot and bright and ended their brief lives in spectacular supernovae or by collapsing directly into black holes. Thus, early galaxies were chemically simple but physically intense. Gas collapsed rapidly, forming massive stars at prodigious rates. These stars then flooded their surroundings with blistering ultraviolet radiation and powerful stellar winds. Supernova explosions followed in just a few million years, shock heating the gas, seeding it with the first heavy elements, and stirring the young galaxy violently. Stability was not an option. Rapid, chaotic growth was the rule. Another invisible but essential player in this drama is dark matter. Dark matter does not emit, absorb, or reflect light. It interacts with ordinary matter and radiation primarily, and perhaps only through gravity. Yet its gravitational influence is the cosmic scaffolding upon which all structure is built. Observations show that dark matter outweighs ordinary matter by a factor of about 5 to 1. In the early universe, dark matter clumped first, forming vast, diffuse halos. The gravity of these dark matter halos provided the wells into which primordial gas could flow, cool, and eventually form stars. Without dark matter's gravitational pull, the gas would have remained too diffuse, and galaxies would have struggled to form at all in the time available. With dark matter, structure could emerge efficiently even when the universe was young and expanding rapidly. This role of dark matter is not a speculative add-on. It is grounded in multiple independent lines of evidence, from the rotation curves of modern galaxies to the detailed patterns in the cosmic microwave background, painstakingly mapped by missions supported by NASA, ESA, and other agencies worldwide. In the context of the earliest galaxies, dark matter provides the essential, invisible framework. Within these halos, gas settled, cooled, however inefficiently, condensed, and ignited the first stars. The properties of the earliest galaxies, their sizes, their masses, their growth rates, were therefore deeply connected to the properties of their host, dark matter halos. This theoretical picture led astronomers to expect certain telltale signatures in the first galaxies. They should be compact, with their stars and gas packed into a relatively small region. They should appear clumpy and irregular, lacking the smooth disks or bulges of mature galaxies. Their light should show the signatures of intense star formation, hot, massive stars producing strong ultraviolet and infrared emission, and they should be seen evolving rapidly, with evidence of mergers and dramatic changes over relatively short cosmic timescales, tens or hundreds of millions of years, which is fast for a galaxy. For years, these expectations could only be tested indirectly and incompletely. Hubble and other great observatories could glimpse the very distant universe, but the galaxies appeared as those faint, reddish smudges. A faint blur could be many things: a genuinely primitive, small galaxy at the edge of time, a more mature but dusty galaxy at a middle distance, or even a chance alignment of closer objects. Without the ability to take a detailed spectrum or to see its structure clearly in infrared light, it was incredibly difficult to tell what you were truly looking at. This is the frontier where James Webb's observations become truly decisive. With its large, cold, infrared-optimized eye, Webb does not just see these objects as slightly brighter smudges. It begins to resolve them. Shapes that were once indistinct blobs now show internal structure. What looked like a single point of light might resolve into 3 or 4 bright knots of star formation. Compact cores emerge from the noise. Irregular, elongated, or chain-like shapes become visible. In many of Webb's early deep-field images, the most distant candidates do indeed appear small and chaotic, just as theory predicted. Their infrared colors are consistent with the light of young, massive stars, heavily redshifted. Even more powerfully, when Webb turns its spectrographs on these candidates, the data often confirms the story. Spectra reveal the telltale fingerprints of elements like hydrogen and oxygen, but with a striking absence of the stronger metal lines seen in older galaxies. The inferred star formation rates are often extraordinarily high for the galaxy's small size. In these cases, observation and theory align beautifully, giving scientists confidence that they are indeed seeing galaxies as they were only 400 to 500 million years after the Big Bang. But Webb has also delivered surprises, as any powerful new tool should. Some of the early galaxies it has identified appear to be brighter, more massive, and more structurally evolved than the simplest models had anticipated for such early times. A few candidate galaxies at extremely high redshift seem to contain the mass of tens of billions of stars already, rivaling smaller, modern galaxies in an era when the universe was less than 5% of its current age. Their spectra sometimes show signs of a more complex chemical enrichment than expected. These observations have sparked intense discussion and debate within the cosmology community. Do these objects imply that star formation and galaxy assembly got off to a much faster start than we thought? Do they challenge our understanding of how dark matter halos formed in the very early universe? Or, and this is always the first question scrutinized, are there subtleties in how we estimate these galaxies' distances and masses from the current data? Could some be slightly closer, their light amplified by the gravitational lensing of foreground galaxy clusters? Could their light be contaminated by brighter foreground objects? Could assumptions about their stellar populations lead to overestimates of their mass? These questions are not signs of failure or crisis. They are the vibrant signs of a healthy, active science operating at its frontier. When observation confirms theory, confidence in our understanding grows. When observation challenges expectations, it forces the understanding to deepen, expand, and become more nuanced. The goal of science is not to preserve models unchanged, like religious dogma. The goal is to refine models until they describe reality more accurately, even if that means letting go of simpler, more elegant initial ideas. The early results from Webb are now driving a new cycle of theoretical work and more detailed observational campaigns. Simulations are being rerun with adjusted parameters. Perhaps gas cools more efficiently in dense pockets. Perhaps the first stars formed in bursts that were even more prolific. Perhaps early black holes played a larger role in lighting up these galaxies. Each possibility is explored. What is emerging from this dynamic interplay is a picture of the early universe that is even more dynamic and diverse than previously imagined. Cosmic dawn was not a uniform, gentle brightening. It was a patchwork, a flickering into existence of brilliant knots of light in a sea of darkness. Some regions, perhaps seeded by unusually dense ripples from the Big Bang, lit up astonishingly early and rapidly. Others took longer to get started. Galaxies did not wait patiently to mature in isolation. They grew through a violent, messy process of rapid gas accretion, furious star formation, and frequent mergers. Many of the grand galaxies we see today, including our own Milky Way, have their roots in this restless, chaotic era. This is why astronomers increasingly speak of cosmic dawn, not as a single moment when a switch was flipped, but as a period, a protracted transition that may have lasted several 100 million years. James Webb's great power is that it can map this transition. It can find galaxies at slightly different redshift snapshots from different moments in this dawn. By comparing them, astronomers can begin to reconstruct a sequence. Here is a galaxy just turning on its first major burst of stars. Here is one 100 million years later, already showing signs of enrichment from its first supernovae. Here is one that appears to be undergoing a major merger, its shape violently distorted. This approach shifts the focus away from the sensational but scientifically nebulous hunt for the very first galaxy, and toward the more meaningful reconstruction of the processes that governed universe's transition from darkness to light. It shows how complexity emerged from simplicity, how structure arose from near uniformity, and how the universe learned to build the engines of light that would eventually make it observable. As the earliest galaxies come into sharper view, cosmic dawn reveals itself not as a sudden flash, but as a slow, uneven sunrise, illuminating a landscape of incredible activity and change. And at the very threshold of this dawn, just beyond the reach of even Webb's penetrating gaze, lies the deeper darkness that preceded it. The cosmic dark ages, and the mysterious population of the very first stars. It is to that final frontier of starlight and the limits it imposes that we must now turn. Before the first stars formed, the universe was dark in the most literal sense imaginable. Not empty, not inactive, but utterly unlit. For millions of years following the release of the cosmic microwave background, the cosmos was a vast, expanding sea of neutral hydrogen and helium gas, threaded with dark matter and still echoing with the faint afterglow of its own creation. There were no points of brilliance, no stellar furnaces, no sources of visible or ultraviolet light to pierce the profound blackness. This long, silent interval, stretching from about 380,000 years to roughly 400 million years after the Big Bang, is known as the Cosmic Dark Ages. It is a chapter of the universe's story written in shadow, its events hidden from direct view because the primary actor, light, was not yet present to record them. Cosmic dawn marks the end of this darkness. It is the epoch when the first stars ignited, switching on the universe's earliest sources of luminous energy. But this was not a single instantaneous event, like a cosmic light switch being flipped. It was a gradual, uneven transition spread across time and space, as the first pockets of gas finally became dense enough to collapse under their own gravity, heat up to staggering temperatures, and trigger the nuclear fusion reactions that define a star. Those first stars, known to astronomers as population 3 stars, were unlike anything that shines in the night sky today. Modern stars, including our Sun, form from gas clouds already enriched with a mix of heavier elements, carbon, oxygen, iron, silicon, the ash, from countless generations of stellar lives and deaths that came before. This chemical richness is crucial. These metals, as astronomers call all elements heavier than helium, act as efficient radiators, allowing the gas cloud to cool, fragment, and condense into stars of various sizes, from small red dwarfs to massive blue giants. The earlier stars had no such legacy. They formed from gas composed almost purely of primordial hydrogen and helium, the simplest elements forged in the universe's first 3 minutes. Without heavier elements to help radiate away gravitational energy, this pristine gas behaved differently as it collapsed. It resisted breaking into many small clumps. Instead, theoretical models and sophisticated simulations suggest it tended to collapse into much larger, monolithic structures. As a result, population to third stars are thought to have been true cosmic titans. Many likely weighed tens, if not hundreds of times the mass of our Sun. With such enormous mass packed into a single object, their cores burned at ferocious temperatures and pressures. Nuclear fusion proceeded at a furious prodigal rate. These stars would have shone with a brilliant, blistering blue-white light, pouring out immense amounts of ultraviolet radiation. But this brilliance came at a steep cost. Massive stars live fast and die young, while a star like the Sun can shine steadily for 10 billion years. A population third star with 100 solar masses would exhaust its hydrogen fuel in only 2 or 3 million years, a cosmic blink of an eye. Their lives ended either in spectacular supernova explosions that utterly destroyed them, or, for the very most massive, in direct collapse into black holes. This fleeting nature is a primary reason they are so elusive to direct observation. By the time their light reaches us across 13 billion years, the individual stars themselves are not just dead, their material has long since been recycled into later generations of stars and planets. Even if we could look back to the exact moment they shone, they were embedded within dense, opaque clouds of primordial gas, their light lightly absorbed and reprocessed by their surroundings before it could escape into intergalactic space. For any telescope, spotting a single, first-generation star across such a gulf of time and space is extraordinarily, perhaps impossibly, unlikely. They are like mythical giants, whose existence we infer from the footprints they left behind, not from glimpsing their forms directly. But the absence of a direct sighting does not mean an absence of evidence. The influence of these first stars is written indelibly across the subsequent evolution of the cosmos. One of the most profound clues they left is in a state of the universe's gas. The intense ultraviolet radiation from massive population 3 stars was energetic enough to rip electrons away from the nuclei of hydrogen atoms, a process called ionization. This transformed vast regions of neutral, opaque hydrogen into ionized, transparent plasma. Think of it as a cosmic defogging. As more of these first stars ignited, their spheres of influence bubbles of ionized gas grew and began to overlap. This epochal transformation of the universe from neutral to ionized is known as reionization. It was not a gentle process. It was a fundamental change in the universe's very state, a phase transition driven by starlight. Reionization marks the moment when light truly began to travel freely across cosmic distances, clearing the pathways that would eventually allow the light from later galaxies to reach telescopes like Hubble and Webb billions of years in the future. Another lasting imprint is chemical. The first stars were the universe's first nuclear forges for elements heavier than helium. In their cores and in their violent deaths, it created the first carbon, oxygen, nitrogen, and iron. When they died as supernova, they scattered these newly forged metals into the surrounding gas. This enrichment changed the rules of the game forever. Even a tiny trace of these elements allows gas to cool and fragment much more efficiently. The next generation of stars, formed from this slightly enriched gas, could therefore be smaller, longer-lived, and more diverse. This is why the Sun, a later generation star, contains about 1.4% heavier elements. The first stars thus seeded the universe with the raw materials for rocky planets, organic molecules, and, ultimately, life. They transformed the cosmos from a simple two-element soup into a chemically rich and complex environment. Astronomers search for this legacy by studying the composition of the earliest galaxies Webb can see. Spectroscopic measurements are key. A galaxy spectrum showing extremely weak or absent metal lines suggests it is very young, containing only the first or second generation of stars. A spectrum with faint but detectable metal lines indicates it is slightly more mature. Some of its gas has already been cycled through an earlier stellar generation. By measuring these chemical fingerprints, astronomers can begin to construct a timeline of enrichment, piecing together how quickly the first stars polluted their surroundings. Observations supported by NASA, ESA, and other agencies are turning galaxies into archaeological sites. Where the chemical abundance is a fossil record of earlier stellar activity, there is also evidence in the very way early galaxies shine. Even if we cannot isolate a single population 3-star, the collective light of a galaxy dominated by such massive stars would have a distinctive signature. Their hot, massive nature means they produce an enormous amount of high-energy Lyman alpha ultraviolet radiation. However, the neutral hydrogen that still filled the universe during reionization strongly absorbs this specific wavelength. Therefore, one key prediction is that galaxies in the heart of the reionization era should show a sharp dropout or attenuation in their light at the Lyman alpha wavelength. Webb is exquisitely tuned to search for this signature. Furthermore, the overall shape of a galaxy's spectrum, its continuum, can reveal the temperature of its stars. A spectrum tilted strongly toward the blue indicates very hot, massive stars, hinting at a population reminiscent of those first giants. In this way, the first stars announce themselves indirectly through their transformative effects, rather than their direct glow. Cosmic dawn, therefore, is not merely about stars turning on like isolated light bulbs in a dark room. It is about the universe becoming chemically, dynamically, and radiatively active for the first time. Light began to travel freely. Gas changed its fundamental state. Structure grew more complex. Perhaps most importantly, the universe's overall transparency began to change. Before the first stars, the universe was largely opaque to energetic ultraviolet light. Neutral hydrogen acted as a potent absorber. As stars formed and ionized their surroundings, this fog lifted region by region. Light could propagate, information could travel. Star formation did not merely add sources of illumination, it altered the very medium through which illumination moved. This gradual clearing of the cosmic fog was uneven and extended. It did not happen everywhere at once. Some regions, perhaps seeded by unusually dense concentrations of dark matter, lit up early, creating large ionized bubbles. Other regions remained neutral for longer, pockets of the primordial darkness holding out against the advancing light. Reionization likely spans several 100 million years, a protracted cosmic struggle between the forces of illumination and absorption. Understanding this helps clarify why the first stars are better thought of as a population, a collective phenomenon whose combined impact mattered far more than any individual star's brief, brilliant life. It also explains why modern telescopes like Webb focus so heavily on detecting the consequences of early star formation. The ionized gas, the chemical signatures, the altered galaxy spectra, rather than on the quixotic quest to image the stars themselves. There is a quiet elegance to this indirect approach. Rather than demanding to see the mythical giants directly, astronomers listen for the echoes they left in the fabric of the cosmos. They read the changes written into the state of the gas, the patterns in the light, and the chemistry of ancient galaxies. They reconstruct events that happened over 13 billion years ago, from subtle traces preserved in the data, like fossils in stone. Cosmic dawn, in this richer sense, is not just a moment in time. It is a transformation of the universe's very character. Darkness gave way to structure, simplicity gave way to complexity, isolation gave way to interconnection, and as star formation spread, it set the stage for an even larger narrative, the assembly of galaxies and the creation of the environments where life could one day arise. The process of reionization is so central that it warrants a closer look, as it represents one of the last major phase transitions in cosmic history and defines a fundamental horizon for observation. After the universe cooled and neutral atoms formed, giving us the cosmic microwave background, it entered the Dark Ages. The gas was neutral. Then, as the first stars and later, the first galaxies switched on, the radiation began to carve out ionized bubbles. Imagine a block of ice slowly melting from the inside, with liquid pockets growing and merging until the entire block is water. Reionization was like that, but in reverse. Islands of neutral gas were gradually eroded by the advancing fronts of ionizing radiation. Studying this process is incredibly challenging because it involves mapping the state of diffuse hydrogen gas across billions of light years and back in time. Astronomers do it by using distant galaxies and quasars as backlights. When light from a very distant galaxy travels through the intergalactic medium on its way to us, the neutral hydrogen it encounters will absorb specific wavelengths, creating a dense forest of absorption lines in the galaxy's spectrum. The characteristics of this Lyman alpha forest depend on how much of the hydrogen is neutral versus ionized. By taking spectra of galaxies at different redshifts, that is, from different slices of time, astronomers can chart how the absorption changes. During the heart of reionization, the forest becomes so thick at certain wavelengths that it creates a complete absorption trough, effectively blocking the galaxy's light entirely at wavelengths shorter than Lyman alpha. This is the Lyman alpha dropout that serves as a key tool for finding extremely high redshift galaxies. As reionization ends and the universe becomes fully ionized and transparent, the absorption trough becomes less severe, and Lyman alpha emission from the galaxies themselves can shine through. James Webb is a revolutionary tool for this investigation. Its infrared capabilities are perfectly suited to detect the redshifted Lyman alpha feature from galaxies in the reionization era, redshifts from Z6 to beyond Z15. By conducting deep spectroscopic surveys, Webb can measure the fraction of galaxies that show strong Lyman alpha emission at different epochs. A sudden increase in the visibility of Lyman alpha emission at a certain redshift would signal the point where the universe became mostly transparent, marking the end of reionization. Furthermore, Webb can study the detailed properties of the galaxies themselves during this era, their sizes, luminosities, and star formation rates to understand what kinds of objects provided the photons that drove reionization. Were they numerous small galaxies or a few bright massive ones? The answer has profound implications for our understanding of early structure formation. This work is complemented by other probes, including the subtle polarization patterns in the cosmic microwave background, which carry an imprint of the scattering of photons off electrons released during reionization. Satellite missions like ESA's Planck have provided exquisite data on this, suggesting reionization was a drawn-out process concluding around redshift Z6, or about 1 billion years after the Big Bang. Webb's observations are now providing the crucial, direct evidence from the galaxies that caused it, tying together the story from both the background radiation and the foreground sources. Reionization also marks a philosophical shift in cosmic history. It represents the moment when light stopped being a local phenomenon and became a global, structuring force. Individual stars no longer illuminated only their immediate cocoons of gas. Their combined influence altered the state of the universe at large. The early universe moved from a state of isolated dark pockets toward an interconnected, transparent cosmos, where light could weave a web of influence across vast distances. Understanding this era helps place the ultimate limits on how far observation can reach. Before reionization, light from the earliest sources struggled to travel far. It was repeatedly absorbed and re-emitted. Its information scrambled, There is a fundamental horizon, a wall of opacity that separates us from the Dark Ages. No telescope can see through that wall using starlight because the starlight itself could not travel through it unimpeded. These limits are not imposed by our technology. They are written into the timeline of cosmic history by physics itself. James Webb's observations approach this boundary with exquisite care. They explore the universe during and just after reionization, a time when the cosmic fog was lifting. In doing so, they bring astronomers closer to the earliest possible light that can still be observed directly, not to the absolute beginning, but to the edge where observation becomes feasible. Reionization, then, is not just another chapter. It is a gateway. It marks the moment the universe became largely visible on the largest scales. The moment light began to travel far enough for deep-time observation to exist at all. Beyond it, looking further back in time, lies the darkness of the Dark Ages. Not because nothing existed, but because light could not yet carry the story forward in a coherent stream. As observation reaches farther back, it eventually encounters a boundary that cannot be negotiated, a limit that is not a blur to be sharpened with better optics or a gap to be filled with future engineering. It is a genuine, physical limit set by the universe's own development. Beyond a certain point, there are simply no stars or galaxies to observe. There are no luminous structures, no concentrated sources of light at all. This boundary is defined not by distance alone, but by history. It marks a time before the universe had learned how to shine. This period, the cosmic Dark Ages, is a known silence. From an observational perspective, that silence is profound and defining. Telescopes detect light. They cannot detect what does not emit. No matter how sensitive an instrument becomes, it cannot collect photons that were never produced. This is the hard, impassable observational limit for astronomy as we know it. The universe does not offer an infinite archive of visible history. It offers a finite window, and that window's shutter opened with the ignition of the first luminous objects. Everything before that moment resides permanently beyond the reach of direct observation by starlight. Understanding this helps clarify what it truly means to ask how far back a telescope can see. The answer is not simply a measure of engineering ambition or mirror size. It is determined by the moment the universe began producing light that could travel freely. The James Webb Space Telescope was designed to approach this boundary as closely as physics allows. By detecting faint infrared light from the earliest galaxies and the final stages of the first star formation, it observes the conditions just after the end of the Dark Ages. It can study the early stages of cosmic dawn in stunning detail, mapping how light began to spread and transform the cosmos. But it cannot see before that. There is no setting, no filter, no mode on the telescope that would allow it to peer into a universe with no stars. This is not a shortcoming of Webb. It is a reflection of a fundamental reality. Sometimes, limits are framed as challenges to be overcome. In this case, the limit is the phenomenon being studied. The absence of light is itself a critical part of the universe's story. The cosmic Dark Ages are observable only in an indirect, inferential sense. Their presence is felt through what follows: the timing of the first galaxy formation, the state of the gas as revealed by reionization. The required conditions for luminous structural point logically back to a prolonged period of darkness that preceded them. Astronomers can model this era with considerable confidence because it follows from well-understood physics, gravity acting on slight density variations in an expanding, cooling soup of gas and dark matter. The absence of stars is not an assumption. It is a necessary stage, a period of gestation before birth. This distinction is vital. The Dark Ages are not mysterious because they are unknown. They are quiet because nothing was shining yet. They are the universe preparing the stage, and we understand the preparations well, even if we cannot watch them happen. James Webb's observations press right up against the end of this silence. They explore the transition from darkness to light, when the first stars began to alter their surroundings and observation via starlight became possible. But just beyond that transition lies another, even more ancient boundary. Even before the first stars, the universe was not completely opaque to all light. For the first 380,000 years, It was a searing, dense plasma, filled with light that was trapped, constantly scattering off free electrons. As the universe expanded and cooled past a critical point, electrons combined with nuclei to form neutral atoms, and the trapped light was suddenly set free. That event released a flash of radiation in every direction, the cosmic microwave background, CMB. This is the oldest light we can ever hope to observe directly. It does not come from stars or galaxies, it comes from the universe itself, from a time long before any luminous structures existed. It is the afterglow of the hot Big Bang, a fossil from the infant cosmos, now cooled to a faint microwave whisper just 2.7 degrees above absolute zero. James Webb cannot observe this radiation. Its instruments are tuned to the near and mid-infrared, the domain of stars and galaxies. The CMB resides at much longer microwave wavelengths, requiring different kinds of telescopes altogether, like the Planck satellite or ground-based microwave dishes. This separation is intentional and logical. Different questions demand different tools. The existence of the CMB marks the ultimate observational horizon for electromagnetic astronomy. Beyond it lies a universe that cannot be seen with light at all, not because it is hidden, but because it predates the transparency of the universe itself. Before the release of the CMB, the cosmos was an opaque fog. Photons could not travel in straight lines, and no image of that era can reach us. That early, ultra-hot state is studied through its indirect consequences. The large-scale structure it seeded, the elemental abundances it produced, and through theoretical extrapolation, but never through direct imagery. Understanding this layered set of limits brings a final clarity to the idea of seeing back in time. First comes the limit of star formation. Before stars, no starlight. Then comes the limit of transparency. Before the release of the CMB, no free-streaming light at all. Each boundary is imposed by physics, not by our current technological capability. Technology can approach these limits, peer right up to them, and extract every last photon from the eras just on our side of them. But it cannot erase them. This realization is not discouraging. It is grounding and illuminating. It tells us that the universe is structured in a way that makes certain eras fundamentally accessible to direct observation and others fundamentally inaccessible. Knowing where those boundaries lie helps focus scientific effort where it can be most productive. It prevents futile quests and clarifies what questions can be answered with which tools. James Webb's majestic role is to explore the last luminous threshold, to observe the earliest stars and galaxies, to study how light first reshaped the universe, and to map the great transition from darkness to complexity. Beyond that, astronomy gracefully hands off to other disciplines, to theoretical cosmology, to particle physics, to the study of the CMB, and to the indirect inference of conditions from their later effects. This division of labor is a strength, not a weakness. It allows each tool to be used where it works best. The cosmic dark ages remain dark, not because they are hidden from us, but because they were never illuminated. The cosmic microwave background remains the oldest light because it marks the moment illumination, in the form of freely traveling photons, became possible. Together, these boundaries define the edge of the observable universe in time. James Webb stands silently at that edge, a sentinel in the cold dark, listening with unimaginable patience for the faintest echoes of the first stars. It does not promise to reveal everything. It promises to show us exactly how far light itself allows us to look. And in doing so, it performs a service more valuable than any endless extension of vision. It defines the frontier. It shows us where the map ends. And in that act, it gives meaning and scale to everything within the map. The telescope reminds us that some limits are not obstacles to be overcome, but features that give the universe its shape, its history, and its narrative depth. To know the limit is to truly begin to understand the vast, structured, and luminous expanse that lies within it. When people imagine the edge of the observable universe, they often picture a kind of wall of vast, spherical boundary, enclosing everything we can see, beyond which there is either nothing or something forever unknowable. But this picture, born of our terrestrial intuition for edges and containers, is profoundly misleading. The observable universe is not a boundary. It is a horizon. A boundary implies a place you could reach if you traveled far enough. a limit you could touch. A horizon is different. It is defined by perspective and limitation. It marks the limit of how far information has had time to reach us, not the limit of reality itself. From our specific point in space and time, in a universe of finite age where information travels at a finite speed, there is a cosmological horizon. It contains every point from which light has had time to arrive since the universe became transparent. That definition is rooted entirely in physics. The speed of light, the age of the universe, and the stretching of space itself. Beyond this horizon, there is almost certainly more space, more galaxies, more structure, perhaps even variations of physical law or configurations of matter we cannot imagine. But no signal, no photon, no influence from those regions can reach us yet. And for some of them, due to the accelerating expansion of space, they never will. It is not a matter of waiting longer or building a bigger telescope. It is a permanent feature of our cosmic circumstance, a consequence of how space-time evolves. This idea can feel unsettling at first. It suggests that reality extends beyond what can ever be observed, that there are places, entire cosmic domains that exist without any possibility of direct contact or confirmation. But this is not an error in our understanding or a flaw in the universe's design. It is an inevitable feature of a cosmos governed by relativistic physics and undergoing accelerated expansion. The observable universe is defined by causality. It includes everything that has been able to influence us, to send a signal that could arrive at our location by now. Outside it lie regions that are causally disconnected, not because they are hidden behind a veil, but because the structure of space-time itself prevents any interaction. They are over the horizon in the most fundamental sense. This distinction matters deeply when we consider the role of our most powerful observatories. The James Webb Space Telescope dramatically improves our ability to see faint and distant objects. It allows astronomers to study galaxies whose light has been traveling for over 13.5 billion years, bringing us images from when the universe was less than 300 million years old. It pushes observation to the very precipice of the luminous universe, but it cannot redefine the horizon itself. Webb cannot make the observable universe larger. It cannot bring permanently unreachable regions into view. What it can do with breathtaking precision is reveal the detail and complexity of what lies within our horizon, especially near its edge in time. It sharpens our understanding of the last visible chapters without moving the final page. This helps clarify what true progress in astronomy means. Advancement is not about erasing limits or extending vision infinitely. It is about approaching those limits honestly, mapping them with increasing accuracy, and understanding the universe within them more completely. The horizon remains where physics places it, a silent testament to the rules of the game. There is an important conceptual shift here. Instead of thinking of the observable universe as an incomplete picture or fragment of a larger whole we wish we could see, we can think of it as complete in a specific, profound sense. It contains the entire causal history that has led to us. Every event, every star's birth, every galaxy's collision that has had any chance of influencing our location in space-time is, in principle, encoded within our past light cone. Everything that shaped our existence, from the synthesis of the first carbon atoms in an early star to the gravitational perturbations that led to our solar system's formation, is contained within what we can, in principle, observe or infer. Beyond a horizon lies reality that exists independently of our observation, but it is a reality that has not and cannot participate in our causal story. This does not diminish the significance of what we can see. It defines its meaning. Our observable universe is not a random slice. It is our entire historical light cone, the sum of all possible evidence available to us. Understanding that some regions are fundamentally unobservable does not diminish science. It sharpens its focus and grounds its claims. Science is not the pursuit of total, godlike access to all information. It is the pursuit of accurate, evidence-based description within the domain that is accessible. Recognizing our limits prevents speculation from drifting into untestable assertion. It forces curiosity to be channeled into questions that can be answered with the tools of physics and observation. Astronomers are deeply comfortable with this restraint. It is well understood that certain questions, what lies beyond the observable universe, or what happened at the exact moment of the Big Bang, cannot be answered through direct observation. They may be addressed through the elegant mathematics of theory or the logical inference of cosmology, but they cannot be seen. This acceptance allows intellectual energy to focus on what can be learned reliably from the torrent of photons that do arrive. James Webb's monumental contribution fits seamlessly within this philosophical framework. By extending observation closer to the temporal horizon than ever before, it fills in missing chapters of our causal history without claiming to reveal the unreachable. It shows us, in exquisite detail, how structure emerged from near uniformity, how light spread and transformed the cosmos, and how complexity developed within the domain that was destined to lead to us. In doing so, it brings the horizon itself into sharper conceptual focus. The more clearly we see and understand the edge, the more meaningful and rich the story within it becomes. This perspective also encourages a quieter, more profound form of wonder. Instead of fixating on what we cannot see, a recipe for perpetual dissatisfaction, our attention turns to the staggering richness of what we can. The observable universe is vast beyond human intuition. It contains 2 trillion galaxies, each with billions of stars, unfolding across 13.8 billion years of narrative time. That this entire expanse is accessible to our reason and our instruments at all is a remarkable fact. The horizon is not a denial. It is an invitation to think carefully about scale, causality, and the very nature of knowledge. It reminds us that knowledge grows not by ignoring boundaries, but by mapping them with ever greater precision. As observation approaches its furthest reach, the task becomes less about discovery in the dramatic, pioneering sense and more about synthesis, about understanding how all the pieces of the cosmic story fit together within the space that can be known. This sets the stage for a final reflection rather than a final revelation. The true edge of the observable universe is not a cliff edge, but a gentle fading, a deepening redshift where signals weaken, timelines stretch, and information slowly dissolves into the background noise of creation. It marks the transition where recorded history gives way to informed inference, where observation hands off gracefully to theory. Standing at this edge, supported by the engineering marvel of Webb, does not provoke alarm or frustration. It encourages a profound perspective. It shows that the universe is larger than what can be seen, and that seeing is only one mode of knowing among many. The light stops, but understanding continues, built on the foundation of what the light has told us. By the time all the pieces are laid side by side, the finite speed of light, the stretching of space, the formation of the first stars, the era of reionization, the cosmic microwave background, the question of how far back James Webb really sees, becomes clearer, quieter, and more profound than it first appeared. There is no single dramatic cutoff, no sharp line where vision fails. Instead, there is a layered set of limits, each grounded in physics, each telling a part of a coherent story. The first limit is observational. Light must exist to be seen. Stars and galaxies must form before they can emit. Webb looks back to a time when the universe had already begun to light itself, when the first luminous structures were emerging from the darkness. It does not see the beginning of everything. It sees the beginning of light as a cosmic narrative force. This distinction is crucial. The origin of the universe, the Planck epoch, the inflationary moment, these lie beyond direct observation by any telescope. They are inferred through the logical consistency of theory and the indirect fingerprints they left on the CMB and large-scale structure. Observation, in the sense of collecting photons from events, begins later, when the universe became transparent and when sources switched on. Webb occupies a precise and privileged position in this timeline. It observes the universe after the cosmic dark ages, during and after the formation of the first galaxies. It captures light that has traveled for more than 13 billion years, stretched into the infrared by expansion, thinned by unimaginable distance, and preserved just long enough to be intercepted by its gold-plated mirrors. That is an extraordinary reach, but it is not unlimited, and it was never intended to be. The physical limits do not compete with each other, they interlock and reinforce a single, consistent picture. The finite speed of light ensures distance and time are woven together, Cosmic expansion stretches wavelengths, shifting early light into the infrared. The formation of the first stars defines when luminous signals begin. The transparency of the universe, achieved first at the release of the CMB and later solidified after reionization, determines how far those signals can travel. The accelerating expansion of space sets a causal horizon on our future and defines which regions of the past remain accessible. James Webb operates at the intersection of these constraints. Its large mirror gathers the faint ancient photons that exist. Its infrared instruments listen where that light now resides after its long journey. Its cryogenic cooling prevents the telescope's own warmth from drowning out the signals. Its location at L2 provides a stable, dark, cold vantage point. Every design choice traces back to a specific requirement imposed by the universe's own rules. Seen in this light, James Webb is not a machine designed to defeat limits. It is a machine designed to respect them, to align with them perfectly. This is the source of its power. By harmonizing its design with the universe as it is, rather than as we might wish it to be, the telescope reaches the furthest point observation reasonably allows. It sees not to the origin of time, but to the earliest chapters where light begins to write a decipherable record, and that record is breathtakingly rich. Webb reveals early galaxies assembling with startling rapidity, stars forming under conditions never seen in the local universe, gas cooling and collapsing in environments of pristine simplicity. It shows structure emerging sooner than some models predicted, and in other cases, behaving exactly as forecast. It provides data that confirms some theoretical ideas, challenges others, and refines nearly all of them. In doing so, it clarifies another vital distinction. Seeing further back does not automatically mean understanding more deeply. Observation provides raw information pixels, spectra, flux measurements. Interpretation requires theory, simulation, context, and patience. The deeper the observation, the more carefully conclusions must be drawn. The more humility must be exercised. Webb does not hand over answers fully formed. It supplies constraints, precise, unforgiving data points that our stories about the early universe must now fit. Astronomers use these constraints to test ideas about early star formation, galaxy growth, chemical enrichment, and the role of dark matter. When observations align with expectations, confidence in our models increases. When they do not, understanding evolves, sometimes in small adjustments, sometimes in more significant revisions. This is not a weakness of science. It is its greatest strength. It is a process that keeps our knowledge alive, dynamic, and responsive to reality. Limits, in this context, are not failures. They are the features of reality that give structure and direction to our inquiry. Knowing where observation must stop allows intellectual and technological effort to be focused where it can be most productive. It prevents the confusion of what can be seen with what must be inferred. The universe is not obligated to be fully observable. Some regions lie beyond the cosmic horizon. Some epochs precede transparency. Some processes leave no direct luminous trace. Acknowledging this does not diminish the spirit of discovery. It sharpens it, giving it honesty and depth. James Webb's contribution, therefore, is best understood not as a promise of total access, but as an act of supreme precision. It defines with unprecedented clarity how far back the observation of starlight truly reaches. It maps the edge of the luminous universe with data rather than speculation. That edge is not the absolute beginning. It is the point where stars first ignited in large numbers, where galaxies began their stately assembly, and where light first became abundant enough to shape the cosmos on the largest scales. Everything before that remains part of cosmic history, but not part of its directly visible archive. This layered understanding brings a sense of calm and completeness rather than disappointment. It shows that science progresses as much by mapping boundaries with care as by exploring the interiors they enclose. It reveals a universe that is generous with information, but not infinite in what it offers to our sight. It invites a curiosity tempered by realism, a wonder grounded in fact. The further back James Webb looks, the more clearly this balance comes into view. Observation reaches astonishing distances. Theory, anchored by that observation, extends further still in its explanatory power. Together, they form a coherent, evidence-based picture of a universe that can be known deeply, meaningfully, even if it cannot be known completely. So, how far back does James Webb really see? It sees far enough to witness the moment light took hold of the cosmos. Far enough to document the universe's transition from dark simplicity to luminous structure. Far enough to test the foundational pillars of modern cosmology with real data from its first chapters. And then, precisely where the light from those first stars and galaxies finally fades into the pre-stellar darkness, it stops. Not because science has failed, but because it has succeeded. It has reached the boundary set by reality itself. That understanding does not close the story. It completes this part of it gently, leaving space for reflection on what it means to explore a universe that reveals itself only where and when physics allows. From here, the task is no longer to push the boundary outward. It is fixed. The task is to listen with ever greater care and wisdom to the story that has already arrived. At the end of this journey, what remains is not a dramatic final revelation, but a clearer, steadier sense of where our vision gently gives way to a necessary and respectful silence. The James Webb Space Telescope was never meant to erase the universe's limits. It was built to bring them into focus. By listening with unimaginable patience to the faintest ancient lights, it has shown us the true extent of our historical view, and, just as importantly, where that view must end. It has clarified the boundary between what can be seen and what must be understood through other means. In doing so, it has made the universe feel larger, not smaller, more structured, not more obscure. Knowing how far back we can see deepens our understanding of everything that lies within that view and gives respectful context to everything that lies beyond. When the edge of observation is mapped with precision, the regions beyond it gain definition rather than mystery. The cosmic dark ages are no longer an imagined, hidden realm waiting to be uncovered by a future, more powerful machine. They are understood as a time before light existed to carry a signal and necessary quiet period in the cosmic story. The earliest moments of the universe are not obscured by secrecy or technological limitation, but by the physics of opacity and the nature of time itself. They belong to a different category of knowledge, accessible to mathematics and indirect evidence, but not to direct sight. This distinction matters. It reminds us that science does not advance by demanding access to everything. It advances by working with meticulous care within the structure that reality provides. The universe reveals itself in layers, and each layer comes with conditions. Light must exist. Space must be transparent. Information must have had time to travel. James Webb respects those conditions. Its power lies not in spectacle for its own sake, but in alignment. It listens where the universe still speaks. It gathers what arrives without claiming to reach what cannot. That restraint is not a limitation of imagination. It is the highest expression of understanding. Astronomy has always been a discipline of patience. Light does not hurry. It travels at its speed, not ours. Signals arrive when they arrive, carrying histories that cannot be rushed. Observations take time. Interpretation takes longer. Confidence grows slowly, through repetition, verification, and the careful revision of ideas. James Webb embodies this pace. Its observations are not instant answers. They are pieces of evidence, accumulated with painstaking effort. Each faint galaxy adds a fragment to a broader mosaic. Each spectrum refines a parameter in a grand model. Over time, clarity emerges not from a single dazzling image, but from the sustained collective attention of the scientific mind. Precision plays an equally central role. At the edge of observation, small differences matter profoundly. A slight shift in a measured wavelength changes an age estimate by millions of years. A subtle spectral feature alters the interpretation of a galaxy's stellar population. A careful calibration prevents the confusion of cosmic signal with instrumental artifact. Precision is not optional when studying deep time. It is the bridge between noise and knowledge, the difference between insight and illusion. Webb's entire design reflects this truth. Its instruments are tuned to listen with minimal interference. Its environment is controlled to reduce contamination. Its data is handled with rigorous care, shared openly, and examined from countless independent angles. This approach reinforces another essential scientific value: humility. The universe does not arrange itself to be easily understood. It does not adjust its behavior to fit our expectations or our hopes. It unfolds according to physical laws that remain consistent, even when their consequences stretch our intuition to the breaking point. Humility in astronomy does not mean a lack of confidence. It means confidence that is earned, bounded by evidence, and always open to revision. It means acknowledging when observation reaches its inherent limit and gracefully allowing other tools, theory, simulation, philosophical inference to take over. James Webb has shown how powerful that humility can be. By clarifying where direct observation ends, it strengthens and refines the role of indirect methods for probing the beyond. It creates a clearer, more honest division of labor within the scientific endeavor. Light tells one part of the story. Other modes of inquiry tell the rest. This balance prevents confusion, keeps interpretation grounded, and ensures that our cosmic narrative is built on a solid foundation. Perhaps most importantly, this entire journey brings a true sense of scale. The universe revealed by James Webb is vast beyond everyday comprehension. Billions of years stretch between emission and arrival. Entire generations of stars live, die, and enrich the cosmos in the time it takes their light to cross the gulf to our telescopes. Galaxies assemble, merge, and transform long before their portraits reach us. Standing within this scale does not diminish human experience. It contextualizes it within an awe-inspiring tapestry. The same physical rules that governed the assembly of the earliest galaxies also govern the chemistry of life on Earth. The same expansion that stretched ancient light into the infrared also shapes the space between stars in our own galaxy today. Time flows forward consistently, whether measured in human heartbeats or in billions of orbits of a star around a galactic core. James Webb's observations anchor this understanding in tangible reality rather than abstract theory. They show that deep time is not just a philosophical concept. It is something that arrives, photon by precious photon, into instruments built to receive it. And then, at the edge, the story changes. The light runs out. Observation stops, not abruptly but naturally, like a conversation fading into a comfortable silence after all has been said. The universe does not slam a door in our face. It simply becomes quiet in a different way. This quiet is not emptiness. It is structure. It tells us that reality extends beyond what can be seen, and that seeing is only one path to knowledge among many. It reminds us that the observable universe is not the whole universe, but it is the entire causal history that could ever influence us directly. That understanding grounds curiosity rather than leaving it frustrated. It allows for wonder without confusion, for questions without the insistence on answers that physics cannot provide. It replaces the boundless urge to push endlessly outward with the deeper insight to look carefully, gratefully, and wisely at what has already arrived. James Webb does not promise to reveal everything. It promises to reveal exactly as much as light allows. In fulfilling that promise, it completes a long arc of human inquiry that began when our ancestors first looked at the stars and wondered what they were. That arc now reaches its natural conclusion at the boundary where vision itself must stop. The boundary is quiet, it is stable, it is defined by the laws of nature, and within it lies a universe of such richness, complexity, and narrative depth that it will occupy the human mind for centuries to come. Knowing where the boundary stands does not close exploration. It makes exploration honest, meaningful, and profound. It leaves the listener, the observer, the thinker, not with unresolved mystery, but with a steady, humbling understanding of scale, time, and the elegant physical rules that shape all observation. The universe does not need to be fully visible to be deeply known. It only needs to be listened to, with patience and precision, where it still speaks. And for now, and for the foreseeable span of human history, it is speaking to us through the quiet, golden eye of the James Webb Space Telescope, telling a story that began billions of years before we existed, a story whose final, faint whispers are just now, finally, arriving home.